means that we need to have guaranteed a SCADE program when it is correct. We need to have guaranteed about what are about the absence of runtime errors. What are the errors that I remain? So when I ask for having safe arrays, I don't want to have, for instance, out-of-bound access. And we want to ensure this determinism that is not in this LUSTRE kernel, as we have seen. So first, let's have a look at how we solve the non-determinism. The case of current actually is a hard case. Well, there is the point of pre, but we can anticipate that pre only introduce one nil, and then we can find a simple way to check if arrows and pre's are well used for that. But for current, there is a real issue that is this one. Actually, a current will provide also a nil for the first steps of a stream that is initially not defined. So I have no value here to L. So there is no initial value in the current. So I have this nil, which are present a number of times that I don't know. And actually, it is arbitrarily complex. It just depends on the properties, on the Boolean properties of this stream here, H. And what we didn't want to use is a model checker to state the correctness of a program. So, well, first because we wanted to be able to specify what is a correct program, and this is something required and important in when you try to when you try to qualify something, to qualify your tool. You need to have a precise specification, and so for that, what we did is that we use classical tools from programming language design that are specific constructs and typing discipline, and we use both to tackle the issue. So the proposition is just to remove current, because we don't really know how to capture this problem, except using a model checker, and to define a dedicated type system to ensure this determinism. So first, the alternative to current is the merge operator that was introduced in this work, so by Marc Pouzet and students, about lucid synchrone. So the idea is that in LUSTRE, actually, you can use current, but if you don't want to fall in this initialization issue, you need to control your access to current with something that implies a clock here. So actually, this is this kind of pattern that you will find in the literature about LUSTRE each time current is used. And the idea is just to capture this kind of thing and make it checked by the clock system. So the merge operator does the following. It takes two streams that are on the complementary clock. So here, when this one is present, the other is absent. And this is guaranteed by the clock checking, and vice versa here. And merge just acts as a selection that builds a sequence that has a faster clock here, using the values from both A and B. In LUSTRE, you will have written this way: if H, then current A, else current B. Actually, semantically, to hold the value, you need practically in your code to introduce a memory. So this one, the version with current introduced memories, while a merge is nothing but combinatorial. You don't have here any memories, just a selection. So in some sense, it is even better for the perspective of the code generation. Then this is the construct, and we need also a type system to support to verify that we are not emitting nils to the outputs. So the principle is very simple. We introduce two types, a type system based on two types. We have the type 1 for a stream that may started with a nil, and the type 0 for a stream that is always defined. And there is this natural subsumption relation that says that an argument, so an argument of type 0, so a stream that is completely defined can always be used, where a stream that is not defined for its first instant is required. And the property checked by this type system is the application never produce a nil on its output. So the type of the pre-operator is the following. It takes a totally defined stream and produce one that is not defined for the first instant. And given this signature, you cannot combine them. Pre of x cannot be typed, which is fair actually, because if you write pre of x, then you get this stream starting with two nils. And there is no way in the language to fill this second nil here. So there is no practical interest in doing it. So except using some, as for the current, I mean, if you use the power of a model checker, then you can do, I will not say anything, but many things, but more things. But we don't want. Yes, and so the arrow operator just takes a first stream with any type, accepts a delayed stream, and provides the type of its first stream. Here is an example. If you have a rising edge detection, an operation that detects rising edges, which is simply checks that the current value of a Boolean stream is true, while it was false in the previous one. You can notice here that there is nothing initialized. So the type for this operator is 0, arrow 1, which means A must be initialized, since I am here delaying it, and the result is not well initialized. And here is the root of my application. Let's suppose it's the root of my application, and I just want to compute the disjunction of two rising edges on two Boolean streams. Then here I have the same kind of signature. I give it to my code generator that implements the check, and I get an error saying that my root node, my root node output must be well initialized, and we see here that it is not. So how can I solve the thing? I can solve it just by providing a first value for this O here. Then I got here the signature that is here, no more delay in the end. And my code generator is now happy. You will notice here that the interest of separating the first value of a stream and the initial value of a memory is that you can decide for the first value here for your whole expression. So this one that each member here is itself defined by this one. So you just define the first value you want and don't really care about the first value of this memory. So this really separates. You put exactly the initial values where you need them. So about the control structures, actually to control the activation of a computation, the clocks are the semantic tool for that, but they are considered hard to use by people. This is something you can also see in Simulink, for instance, to control the computation. They have enabled subsystem which clearly correspond to this construct here. It appears that users prefer to think in terms of activation of a block rather than on present or absent values on streams. Well, so in SCADE 5, this construct was present. Sorry. We did some syntactic rationalization in SCADE 6, but it's nothing more than that. And it expresses this way. But the main drawback of having only this for controlling activation is that each time you want to activate or not, you have to introduce an operator. And by the way, it does not allow to easily share a stream between two different activations. While it's sometimes useful if you think of modes or things like that to share memory between two functions that you activate exclusively. So for that, we introduce scopes and shared memories. So the idea is to have guarded scopes to activate a different set of equations, each set of equations actually defining the same set of stream. And we provide an access to the last value of a stream. So this is not an operator, not really a data flow operator. This is really an access to the value. That's why we put here this quote. And well, just a remark introducing last, you can have introduce a style that is more imperative, let's say, to implement a counter. Well, not a big issue. So the interest of this activation that does not need to introduce an operator is that when you have an algorithm that have different set of equations depending on the case, so you have a case analysis, typically a second degree equation. We have three cases, either the delta is null or is positive or negative, and then for each of them we have different set of equations, and we can just select them this way. So syntactically, we are not a single definition anymore, but semantically we are, since what we guaranteed is that only one of these bunch of equations is active. The question of shared variables. So here I use the graphical notation. So a mix of graphical and textual. So I define the node up and down. And in the up state, I increase, the output are O and P. O is as its last value initialized with 0. So this is this explicit memory I talked before. And we, in the first state, increase it. And P has a definition that looks like a standard counter definition in the old LUSTRE data flow kernel. And when O reaches 5, I enter this state and I start decrementing and so on. And when I reach -5, or 6 actually it is, because it's strict. And what I get if I plot it, I get this two graphs, and we can see that in blue, I have the effect of sharing the memory. This is really a shared state. When I increment here, I reach 6, and then I start decrementing from where I was in the first state here. So really, this last O is the memory that is attached to the scope of O. And while the pre, it's not the case at all. The pre is actually a local memory. And we see we alternate an increasing phase here with a decreasing one, and we just alternate, but there are no communication between both. So the other constructs in SCADE 6 were about safe arrays also. We added a modular reset, which is a construct which is important when you add state machines, because in state machines you want to enter by, you want to resume or reset states, for instance. And of course, hierarchical state machines. Each time you have here references to the paper about that. And so now with SCADE 6, you can design graphically this kind of mix of state machines and data flow, which is, as far as I know, pretty unique. For instance, if you think about Simulink, in Simulink, you have a data flow in which a block can be a state flow, but that's a lift block from the Simulink point of view. Here, you have really a fine mix of both. And in this example, this is a digital watch with several state machines running in parallel with other data flow parts here. So just to resume about SCADE 6 and LUSTRE, we have seen that we have two different kernels here. So what remains the same is the extension of combinatorial operations, the delay, the arrow, the clocks. The current is specific to LUSTRE, and we have replaced it by merge, and we added reset. So these are the two kernels. And actually, if you read papers about LUSTRE, most of the time they only treat this one, which means that clocks are not so well understood by or used by the community. Here is an excerpt of the specification of the real of the qualified code generator. So because we are qualifying it, we need to provide very precise specification. And how to be precise? Let's be formal. Let's try to be formal. That's what we did. In particular, on the static semantic aspect. I mean, all that defines what a SCADE program correct has been formalized. And here, this is the first type system, which is a classic one. So this one just says that arguments are of the right types. And by the way, that array access are within array bounds. So it checks a bit more. This one is about clock checking. So the property it verifies tells us that the program can execute synchronously, and the corollary is that there is no need of to bufferize streams. So it runs in finite memory. We have the guarantee that it runs in finite memory and behaves as expected. The causality analysis that tries to succeed in detecting cycles. And the corollary for that is that the equations can be statically scheduled to produce the sequential code. And the initialization analysis that we discussed earlier. So the organization of the compiler is the following. We have the SCADE language, complete SCADE language. We check all the static properties defined by these 4 type systems here. Then we know it's correct. Once we've established the correctness, we translate the hierarchical state machines into the core data flow, with core data flow that contains the clocks, and reset. And all that is explained in this paper here. And then the data flow compilation that is also detailed in this paper. A few facts about the real implementation. So it's written in OCaml, which was also quite an innovation in this pretty conservative industry. It's not always easy to introduce a new language when people are used to program in C or Ada. So it's about 50 kilolines of code. We had to do some development for specific for that. So a code coverage tool, because standards require to cover the code you are using, producing, and simplify runtime. The formalized static semantics, the formalized part, covers about 100 pages, but all the language is specified, and it's 300 something pages. And it is based on a standard process, so a lot of things, a huge design, many unit tests and reviews. A few words about formal verification. So since SCADE involves a bounded amount of memory, we have a finite state system, and model checking techniques apply. So we have we can verify properties. Properties are traditionally separated in 2 categories: safety and liveness. So here are examples of each. And safety properties can be expressed in SCADE. So you can see SCADE as a modest temporal logic, able to talk about the past. And if you want to prove something, just consists in verifying that a stream does not vary. It's always equal to true. This way to do things was introduced here by Alvax and all. And to do that, in SCADE Suite, we propose a module called Design Verifier that is powered by Prover technology. It's a SAT-based model checker, so you can do bounded model checking or induction and other strategies. The support of arithmetics is now, since the latest version, done by bit blasting all the arithmetic. Make look weird, but it gives good results. And the translation is based on KCG. So here is a paper about induction. And you can find the specification of the input language of this proof engine here. In the industry, formal verification is really something one must have when presenting a new tool to a customer, potential customer. People want to hear something about formal verification, but they still have main difficulties when deploying it. First is that skills of user and the patience. Most of the time they want to have easily and quickly a response, and this is for all those who have used this kind of tool. This is able to make many things and very good things, but there is no magic. You you have to work also. There are also some limited capabilities on numerical aspects. I mean, if your property really depends on complex properties, complex arithmetic properties, then the SAT instances become big, and it may be really hard to solve. So typically, a product gives a very big Boolean circuit. Just think of that as an example. And there is another limitation, that is a lack of clear positioning in the safety standard. I mean that if you are encouraged to do formal verification, but it will not remove anything else in your process. So this is maybe, well, people see more work but no real benefits from the certification authority, from the certification point of view. But there are interesting successes in the railway transportation. So RATP, which is a company managing the Paris Metro. And if you are interested in this topic, I encourage you to click and have a look at these slides about what they do. I have worked on some of these projects, and just to give you figures, it leads to this kind of size for the SAT instances, millions of variables and dozens of millions of clauses. And it can be resolved. Just for fun, some example on the application. Sorry. This is not coming from an embedded system at all. This is an example proposed by Gérard Huet in an old paper where he proposed to prove a magic trick in Coq. So this is an excerpt of the paper. I can just give the rough idea. The idea is to take a card deck where card colors alternate. So you have a red, black, red, black. You split it in two, and you ensure that they started with different colors. And then you just riffle shuffle them, and you get a new deck with a special property that is the following. If you take the cards 2 by 2, you always have a red, black or black, red pair. This is, well, I try to give a picture to explain that. If we generalize it a bit, so instead of considering a finite deck, we just consider a stream, two streams of cards with alternating colors, and one starting with red and the other with black. Then we generalize the property, and actually the property still hold. So we have two sequences, and S1 and S2 for these two here set of cards, these two coming from the two infinite decks. And so the riffle shuffle actually is just the merge operation. You just take a merge and give them a clock that is a random clock, and you're done. So it's quite easy. It's a few lines to capture it and to model it with the kernel we have seen earlier. So we have here the two sequences. One started with false, the other with true, and then just alternate. We merge the sequences, and here we build a stream that is true every 2 ticks, because we need to observe two cards to be able to state the property. So the property is actually half imply the cards are different. So or different from prelude. So this is here written in another way, but basically this is that. And the true here is to satisfy the initialization analysis that is smart, but not enough here in this case. So really the good initialization of that depends on a Boolean property. So this is a typical example of that. And this can be solved by the designed verifier. So another example that is actually something I did 6 months ago. One of my colleagues from an application engineer asked me, well, arrays in SCADE are limited. I don't know if I can implement a vote in SCADE. So the problem is given an array containing pairs of values and validity bits, find the valid values that has the majority amongst the other valid ones. And we all know that counting majorities is still a real issue. So I said, well, I don't know, we can try a naive implementation just to see if we at least can capture the function then. And if the number of, if the size of the array is not too big, maybe it will be okay for your user, but well, let's start with that. So here, this is a very, very naive implementation. Just so you can see here the example involving arrays. So we have the size, the type for the cells. And the naive voter basically computes an array where each cell contains the number of times the value A of I is present in the original array. So it does this sum valid, and sum valid is here, which involves another fold. So once we get that, we can compute the max and then decide based on the max if this max is greater than half of the valid cells, and which is a final condition. So first to be valid, and half of the valid cells, which is a final condition to really have a majority. Well, of course, this is quadratic in N and not good at all. And then I remember that years before, I read a very beautiful algorithm by Boyer-Moore, which is majority. And this majority, so I went through the paper, it's a Fortran implementation of the algorithm. And actually, it's really something that it's just a fold, so something you can implement with the iterators you have in SCADE. So here is the implementation. You can see in the Wikipedia page about the algorithm, how it works. It's quite easy. You have a current candidate for winning, and when if you see it once more time, you increment. If you reach 0, you take the current one as so these are here the cases as the new candidate for winning, and otherwise you increment. But it's not so. There is an intuition, but it's not that easy to figure out why it works. Well, the paper contains the proof if you really want to know it. So the question, I have this naive implementation that I understand, but is not efficient enough, and this one that I don't understand completely, but it's linear. But it's linear. So I can check, for instance, by putting two instances, one for the naive voter and the other for majority, and write the properties. Do they found, is the found stream they compute equivalent? Is the value they found the same? are the values they found the same. And actually, what really matters is that when I found something, I have the same value. Otherwise, just don't found the majority. So I launched the design verifier with these three properties. And the first one is, so the third is valid. The first is valid also here. And the second is not, which means that both algorithms agree when they found, but when they don't found, they don't compute the same thing. So this is an example of using formal verification, for instance, to optimize your code. Actually, this one is rather simple because it's just combinatorial and there are no time in it. So just before I conclude, a few words about the SCADE timeline. Now, what is the history of SCADE? So it's all started in the 80s in the Verimag, around the LUSTRE language. So Nicolas Alvax, Paul Caspi, and Pascal Raymond, Daniel Pilot, started this work. So they define a few versions, and the version 3 has been actually used in an industrial context that was close to the laboratory, Schneider Electric. In the same time, Airbus was using an internal tool set where the ideas were very close to that of LUSTRE, but less, let's say, less academic. I think this was something very common in that year. And so they put all that together and ask a third company to define a product that could be sold to other people. And this and SCADE started here, somewhere in the middle 80s, 90s, sorry. Then, in parallel, Marc Pouzet started his work about lucid synchron with Paul Caspi. And then we started working together. We worked also with STRL. And in particular, the state machines we integrated to SCADE 6 comes from, not directly from STRL, but from the sync chart. That was a graphical notation introduced by Charles André above STRL to program in a state machine style. And this is all the influences for SCADE 6. And actually, the joint work continues. Marc has started interesting in Zelus, which is a hybrid language, so mix of ordinary differential equation and discrete time. And we have an internal prototype that integrates all this idea. And actually, this prototype is behind, is used in the backend of one of the ANSYS tools, digital twin tool. Okay, so as a conclusion, what I call this accomplishment, so we have done we have defined an industrial language with state-of-the-art formal techniques. We have qualified the call generator, and this is actually presently used in more than 200 safety critical systems. So probably each time or the next time, let's see when you will take a plane, it will embed somewhere a few lines of code generated by SCADE. There is a nice typo here. So it is connected to a model checker. The last point is not something I presented here, but it's important since it is required by industrial safety standards, is a definition of notion of structural coverage of SCADE models. So we have defined it and implementing it. The research topics are about, of course, since we started formalizing the language, we would like to go further. So this is still a long-term objective, and to try to go to a mathematical certification with an ITP. This is what was done by Xavier Leroy and his team on a C compiler. And if you like if you are interested in this subject, means the mathematical certification versus the safety standard certification, there is a nice talk from Xavier Leroy here about that. And so this idea of formalizing LUSTRE and the verified compiler was and is actually studied a lot by Tim Burke, and the last important result were given in the thesis of Lelio Brun here. So the other research topics, there is extension of ODE, so the connection to ZILUS, as we see in the previous slide. And we are also challenged by some of our customers that start having a look at machine learning based controllers. So they want to continue to use SCADE to have these certification credits we provide already for an application, but they want us to be able to support this kind of application. And what support means, it's mainly to have an efficient way to deal with arrays and tensors. Well, so this is something we are starting to have a look at and improving what exists already in SCADE. And well, all that is also a long and collaboration with Marc Pouzet. I wanted to say it. Yeah. Thank you. So my last slide is about the SCADE academic program. So if you want to use it for your students, and you can just contact here. And there is a free version also that exists for students. So if they want to train, to do some labs. So it can, everything is from here, started here. Okay. Thank you very much.
Thank you. Yeah, I think we can unmute ourselves for this. Thank you so much for your talk. I have all kinds of questions. I think I could fill an hour with all the questions that I have, but I'll start if you want, and then other people can ask. So my first question is about clocks.
Yeah.
So my understanding is you have a notion of clock, which is a Boolean signal that tells you if the clock is ticking or not. And I guess there is something to be said about the possibility of verifying, because, well, what I have trouble understanding is how much you're going to be able to say about your system when a clock can behave in an arbitrary way. Like, you don't know how frequently it's going to tick. Nothing in the types of the clock will tell you how frequently it ticks, does it? It doesn't tell you the frequency or the delay.
No. This is really a purely logical clock.
Right. So
yes.
I guess my question is, would it make sense to try to analyze the frequencies and the shifts of the clocks based on the numbers that you know should be there?
Yes, sure. It makes perfectly sense. And actually, I did not mention it, but another topic that we have studied is the one of multi-rhythms in application, where you have different frequencies and shifts and so on. And so these are properties that we cannot capture in the clocks when they are only given by arbitrary Boolean expression.
Mm-hmm.
So for that, we have designed an extension that also is inspired and is a simplification of the N-synchronous paper by Marc Pouzet.
Mm-hmm.
So you have just clocks that in the paper. The idea is to have clocks that are expressed as a regular expression, and so you can compare them. And yes, so we have definitely this in one corner of our R&D work, and the goal was to cover the need for having multi-period application that exist in almost every industry.
Mm-hmm. There's a question. I think Manuel has a question. Manuel, can you unmute yourself, or do I need?
Yeah. Can you hear me?
Yes.
Okay.
Sorry, we seem to have had some connectivity issue. Was it just me, or was it everybody?
Yes.
Was for me as
No,
well.
that was for
Yeah.
for
I
me
had the
as
same here as well. Zoom completely went.
Really sorry about that. I don't know what happened.
Never mind.
Okay, so I didn't hear Manuel's question at all. That's when it started failing for me.
Okay, maybe I'll try again. My question is there a relation between the way SCADE or possibly also lucid synchron handle clocks and and determinism or correctness of streams to the different ways how you can do co-induction in type theory? So, for example, there is a theory of clocked types. It's called, I think, by I think Rasmus Møgelsen and it has also clocks on the type level, and you can prove that a stream is productive there. And I was wondering whether that is related, and if yes, how it's related.
I don't know this work, but from what you're saying, yes, it's probably related. So about the co-induction, what I can say is that Marc and Paul Caspi, they have written, I think it's in 98, co-inductive semantics for lucid synchron. So there is this, of course, this definition of streams in a co-inductive way. And also Grégoire Amand, during his PhD, has specified the LUSTRE clocks in coq. So Yes, this is probably related work. I would like to have the reference to see and to read it. If you
Yeah,
can
I'll
send
post
me.
it in the chat in a moment. Yeah.
Okay, so I will have a look.
So I have another question about this. You mentioned that you generate code that is constant in memory usage, correct?
That is, sorry.
I think you said that you generate code. The code generator for SCADE generates code that is has constant memory usage.
Yes. Yes.
Okay, so there's, I guess there's a potential like conflict between memory usage and the ability to go into the past. Because if you have delays, then that means you're essentially looking into the past of a stream. Yeah. And that increases your memory usage.
Yes, but when you generate the code, actually you know statically the amount of memory you need to remember this finite past you need. So this is static information from your code, from your model. Enfin, what I am calling code is your SCADE code. Yeah. If you have one tree, you know that you can generate code with just so this is a unit delay, so you need one
I think we just had the same problem again, didn't we? Yes. I'm really sorry about that. I sent a message to the Splash organizers who are taking care of the video.
Maybe I can just cut the video if
yeah, I think if you cut the video and the sharing, we may be able to. I'm not sure if it's going to help because it seems to be happening on their side, but maybe it's just that Splash is too big a conference and we're overloading the servers. Can you still hear me?
Yes.
So I think you were talking about was it the clocks? Oh no, the code generator.
Yes, code generator. Yeah.
Yeah. Okay. Hey, and I think Wolfgang, I don't know if he's back in. I think he had a question.
I guess it was basically answer my question was also about memory footprint. So because you mentioned the word array, so I assume that the entire footprint of the memory footprint of a program is completely statically known before you start running the code, right?
Yes. Well, it's static. Of course, you have your stack that is statically bounded. What you know about your stack is that.
But you can never allocate any data structures.
No. And this is a principle that is really applied to critical software. This is yeah. That's why the LUSTRE fits well with that idea. But for instance, in Lucid Synchrone, so this second work of Paul Caspi with Marc Pouzet, Lucid Synchrone, it was an ML-like extension of LUSTRE. So you had more functional style higher order and things like that. So it was not static anymore. In LUSTRE, the TRE means temps réel embarqué in French, which is embedded real time.
Mm.
And this aim at being embedded real time really involves this static memory allocation. Yeah.
Thank you.
There's another question from Matisse.
Yeah, thank you. Yeah, thanks for your talk. As somebody interested in data flow languages, it's very interesting to see one that's used in practice. My question is less about the formal aspects, but you mentioned at some point during your presentation that you compile SCADE down to sequential code. Is there any reason why you're not parallelizing this generated program?
So yes, it was mainly for what was asked by the customers. They wanted to execute it on software targets, and were used to implement in C code. So basically, the idea of this code generation was to replace manual coding. And so the first targets were that. The synchronous languages, so in general, were also applied a lot to hardware, where you have this natural parallelism. So, for instance, STRL has done a lot for this domain, so it was more applied and more used for hardware targets. So systems on chip, FPGAs, things like that. And also recently, another kind of extension we did was the multi-core target. So we try to compile and organize the code in a way that can be integrated in a multi-core. We have written a publication about that. It was in FDL 18, I guess. And for the machine learning stuff, we will probably have a look also at GPUs. So we are interested in parallel targets. But the first demands, the first needs were on sequential one. Yeah.
Thank you.
I think we're already way over the end of the session. So if you have to leave, I mean, by all means, I don't want to delay you if you have work. But as you can see, we have all kinds of questions.
Yeah. Okay.
Okay. So I guess we can always send you a message later.
Yes.
If you don't mind. Would that be okay?
I will be connected. Yeah.
Okay. Well, once again, thank you so much for giving the keynote. It was really interesting.
Welcome.
And yeah, we will continue at 10 o'clock, I think is the next session.
4 o'clock.
Oh, sorry. Yeah, we're like at different,
yes,
different time zones. So
I agree, 4 o'clock.
Yeah, so I think the next one will be at 4. Yeah, at 4? Yeah, at 4 o'clock, 10 for me, and I guess 4 for you. So once again, I would like to thank the speaker for the talk, and see you all in.
Thank you.
Hello, Manuel, are you there?
Yes, I am. Hi.
Oh, sorry, I was talking to the other Manuel, the one who is host.
I think. Oh yeah, there is another.
There is another, yes, who is the host right now. But you're giving your talk now. Would you like to check if you can share and everything?
Yeah, sure. Thanks. I will try.
So I'm going to stop sharing my screen. And I think you can
Perfect.
go ahead and share yours. And if you want to turn your camera on, or you can leave it off, it's up to you.
I think screen share should work already. Does it?
Yep, I can see it.
Perfect. Then let's try the camera.
Apart from the loss of connectivity that we had, this is way better than giving talks like in person, in the sense that with the projector, there's always problems, right? And here it's like share screen, it works, done.
Yeah, mostly it works. But yeah, absolutely.
Yeah.
I agree. There is only the thing, especially if you're, I don't know about Windows or Linux, but if you use Zoom for the first time on Mac OS and you start sharing your screen, the operating system asks you to give some permission. And everybody runs into this each time. So
I'm using it on Linux and it's working for me.
all right. Okay, cool.
All right.
As I saw on Clouder, I think we have not been the only ones having problem with Zoom just about 30 minutes ago.
Yeah. I sent a message, but I didn't get any response. So now apparently the YouTube link is working. Okay. You can go back in the stream, but not so much. It also has like limited history, which is funny because we were just talking about it. But yeah, and well, let's see if we get disconnected. I wouldn't be surprised if.
Yeah, keep the fingers crossed for everyone.
Yeah, I think it probably will be. I mean, if you want to turn the camera on, I think that's fine. But I, for example, will probably leave it off most of the time because otherwise, I don't know I don't know what is causing this, but we maybe just all of Splash together, maybe just overloading their system. I don't know.
Yeah, I see your point. Maybe.
I mean, they should be prepared for this kind of thing, but I don't know. Who knows?
Actually, let's give it a try.
Let's everybody turn on all the camera.
Yeah, let's see what
Ivan?
happens.
Yes.
I was under the impression that you're chairing that session and I'm chairing the one two later.
I'm chairing this session, right?
Yes.
Yeah, I'm chairing this session and you're chairing the one later. Yes, but can you make me host? Because I think what happens is when we get disconnected, then it assigns the host completely randomly and I can't reclaim it.
Well, bad luck then for you. No. Yeah, let me try.
I think you just need to right click on me and then say make host or make co-host or something like that. I mean, it's not going to be, there you are. Thanks. Yeah, this stuff about SCADE, like, I didn't know about this until I started working with NASA. And then I started asking around. It's just everybody knows about it. And everybody, of course, knows about LUSTRE. And we're now having this project about converting between, like directly from requirements. No, converting from LUSTRE generated by some model checking tool into C code through Haskell. So we're not using SCADE ourselves because I don't have a license myself. That's the only reason, I guess. But but the principles are similar. So this is super, super useful. Yeah. I wish we could just, spend, it would have been nicer to spend the whole day at the conference asking like Jean-Louis more questions and so on, but I guess the virtual format is also different in that sense. What's that?
Would be really different if you just could catch somebody, right, and have a chat about that stuff.
Yeah.
Rather than having a schedule on their own, and etc.
Yeah. All right. So it's 10 o'clock. I think we can start.
Cool.
All right. So without any more delay, I would like to introduce Manuel Alabor, who is going to talk about the state of debugging for RxJS.
Yeah, thank you very much. Anyway, thanks for having me here and the opportunity to talk to all of you guys. As Ivan already told, my name is Manuel. I'm from Switzerland. I am a front-end engineer for now. I had to look into my LinkedIn profile for more than 7 years now. I've been into web development and working on user interfaces on mobile, also native on mobile for this time. Nowadays, I'm a senior front-end engineer at a Swiss fintech startup. And since a year, I started as a master's student at the Eastern Switzerland University of Applied Sciences. And so my talk here is about the state of debugging for RxJS. And I am pretty sure when I started off with dropping the front-end engineering, you might have thought, oh, front-end engineering, that's this JavaScript thing, right? And front-end engineering, engineers, are these even engineers at all? I think, and I can tell you, especially like things in the title of my talk, RxJS, I'm sure front-end engineering really is an engineering thing nowadays, and it came a long way. So with RxJS, you get your DSL to express data flows within JavaScript. You can do this even with a typed interface today, thanks to TypeScript, which helps a lot if your code base gets bigger and bigger. So all these old jQuery days are gone here, totally. It goes that far that RxJS is a core part of Angular, a web application framework driven by Google. And so, yeah, it allows you to describe data flows as you'd love to do it, right? But then this is not a sales pitch, not at all, because there is another part to this story, and that's about debugging. If I go back to my story, to my history with RxJS, it started for me like, I want to debug, right? So I add a breakpoint with my known tools, like the debugger built into my IDE, try to step through my code. And surprise, surprise, that really does not help that often. It helps sometimes if you're debugging really a Lambda function somewhere in your code, but most often what you are confronted with is something like this, a stack trace, which on the very top has your code, which you're interacting directly with, most probably the stuff you have written, but then below you get all the internal implementations, in this case here of RxJS and the reactive programming runtime environment. And so, yeah, this falls then also short that you can't use step controls. So you would step into the internals of RxJS, which is not that helpful. I, for my part, initially expected so I can jump from transformation to transformation in my data flow graph. of course, afterwards, it's not the way how this tool works. And so I started to use something else most often, and that's the infamous trace log statement. If stuff gets complicated, I was used to and still am used to sprinkle these manual log statements throughout my production code. And in the next step, try to interact with my user interface, get a lot and lots of trace logs in my console, try to make somehow sense of it, hopefully then fix the underlying bug. Of course, then don't forget to remove all the trace logs again, and hopefully not the bug fix I've implemented. And you might already hear it a bit. This left me quite frustrated. I think that's not how a mature software engineering should feel like. That's not productive, it's not efficient at all. So I started to looking into further solutions. And so during my research, I came across of rather elaborate solutions. So for example, the reactive inspector, especially implemented for RE Scala by Salmoneski et al. But then this is made for Scala and RE Scala, of course. There are other smaller utilities like RxFiddle by Banken et al., which helps you to visualize parts of your code. But for doing so, you have, again, extract your code into an additional utility and then run it there so it can visualize the behavior of the data flow. And then something I stuck with till today, it's RxJS Spy. It is a bit a better logging solution for RxJS, but then again, it's still a logging solution. So you have to dig through a lot of trace logs again in your console. And so I was surprised that there is not more good tooling to debug RxJS applications. So I decided I want to change something with this. And back when I started with my master's studies, I came up with 2 research questions for my own work on this. I'm trying to work on this in a more academic way. So before we even can improve something, we need to know what's wrong, right? And so with the first question, we wanted to look into what are the biggest challenges engineers and developers have to face when they debug RxJS applications. And then afterwards, we wanted to give some ideas how a particular problem, a particular challenge could be solved best. And that's what our work here was about. So we did, in essence, 2 qualitative studies. First, we prepared ourselves a bit using interviews and written war story reports. And afterwards, with the main findings out of this preparation, we did a controlled experiment to verify those key findings there. Overall, we have worked with 14 professional engineers during our work. First up, as said, we interviewed and collected written story reports from 10 participants. All of them use reactive programming and are with RxJS daily. We were very lucky to get together with one core team member of RxJS, which we take care for this open source project. And we had defined kind of 2 different scopes for the interviews and the reports. So during the interviews, we wanted to know more in general how people work with reactive programming for web, for backend development, what they like about it, what aspects they don't like about. Of course, we also asked in this, like, how do you debug? But the second part with the reports, this was really about hands-on experiences when they last had to debug some piece of code. What was the problem? How did you proceed to solve this problem? Have you been able to solve the problem at all? And in the end, what kind of tools and techniques did you use for doing so? And we heard repeating themes in this first part of our study. So of course, everybody told us debugging is hard and we don't like it because bugs are bad for us as engineers, right? We're not into the test stuff. So we really like to do things right. And mostly also they told us that using the traditional debuggers coming from imperative programming, it feels unsatisfying. So we had this mentioned 3 times kind of. And then really the big part, what we heard was we use trace logs a lot and we kind of extract code from the production code line into something more specific, into an external sandbox, so we can iterate there faster. So this is like really this whole block of, we called it the manual code modification part, adding trace logs manually or extracting code parts manually and reintegrate after getting the hang on what's wrong there. We had the following key takeaways from this first part. So as said, engineers do a lot of manual code modification when they debug RxJS applications, either by extracting code parts or adding trace logs. And we felt like they do this because the whole tooling they have at hand already in their IDEs, they just can't give them the answer which they are looking for. So like, it's like these traditional tools can't look through the abstractions RxJS provides. And so we came up with this analogy, like if they would have the correct filter, like a matching tool right at their hand, maybe they would do less manipulate their source code manually. And with this, we could improve efficiency and in the end, also the quality of the code they're working with, because they don't have to touch it by hand every time. And so this manual code modification part was the key finding we took further in our study, and we built our controlled experiment upon. Not very surprisingly, it was also the key part to our hypothesis for the experiment. So we really said, if engineers have to debug, they will instrument the code manually, as we saw in earlier answers through trace logs or extracting code to external sandboxes. And so we set up our study. It was also conducted remotely in the spring of this year. We decided to let the subjects execute the experiment on their very own computers. So every subject used their very own and like daily dev routine development environment. And this was crucial to us because we wanted to see how do they really debug as if they would debug in a real situation at work. And so we didn't want to give some specific lab kind of environment for this. During the experiment, we provided them with 2 problems, which they had 25 minutes each to look at. So overall, we had 1 hour for the experiment, and we sent out afterwards an unattended survey where we collected some information about how much experience they had so far with RxJS in particular. Here you see an example of an actual problem we showed to them. So of course they got some code. They also got a unit test suite, which when they first run it, showed some problems. And they were also able to execute a user interface based on the code they got. For us, as where we designed the study, we had the goal, we wanted to see how they debug code. We were not really interested that to solve the bugs, actually, so that was rather frustrating for them. But the task for them was really try to identify and resolve the bugs buried in this program. And by doing so, speak out loud like you would be in a classic pair programming situation, so that we could see the mental process and all the tools they thought about to use, or maybe then refrain from using them. We did our observational study with a total of 4 software engineers. 2 of them told us in the survey afterwards that they currently work with RxJS in their daily job. Most of them, like 3, had more than 2 years of experience with RxJS. And 1 in particular told us they're not doing only front-end work, but also back-end work, most probably with Node.js using RxJS. So based on this information we got from this survey, we had a good starting point that we can compare the observations from the controlled experiment and what they told us they actually use of tools when they debug. And so in the results, we were not surprised that all of them told us they use trace logs to debug, and we could totally confirm this. All of them used it. Where we had already a bit of 2 different answers was regarding the traditional debugger usage. So 3 of them told us we regularly use it, but during the experiment, we could only observe that 2 of them really use those tools. And most surprisingly, 2 told us they really know additional tools to debug RxJS. So like external visualizers, additional logging libraries, such stuff, but none of them used it. So this was really, yeah, we were surprised seeing this, that this was really like going that far aside what people know and what they really do in the end when they're confronted with a problem. Even more, because we gave them the development environment they're used to. So any additional tools they are used to should be present there already, right? So yeah, why didn't they use it? That was stunning for us. We came to the following interpretation. It is never enough that you know about tools. We saw and we felt that the boundary to know something and then really use it is still too high when it comes down to debugging tools for RxJS. So, for example, you needed to install an additional library in order to use it because it was not yet part of the problem we provided to them, or you need to extract some specific code part and bring it to some external sandbox. And so eventually all of them show the tendency and the habit of just adding the trace logs again. And yeah, not going the extra mile necessary to maybe get a more efficient tool to find the problems in the code we provided. And based on this, we find the first answer to our first research question. It's significant to know what tool should be used when, and then of course how to use that tool as well. So often this seems to be the next best, the traditional debugger. Even more often it's modifying the code you have, but less often, unfortunately, it's not using specific tooling. So this brings us to the research question 2 answer. We really want to improve the developer experience in those regards. So lower the boundary to get your hands on the right tool at the right moment when you work with RxJS applications code. And it really has to be where it belongs to. So not an external website, not an external application, anything. It needs to be there where you expect it, because people expect it to be right at the debugger, as we saw also a bit earlier. So it needs to be waiting there and not needing that extra mile to go that they can use it. And with this, can already give a short outlook to the future work, what we are already currently working at. We are currently working on providing a concrete prototype and a concrete solution to prevent this manual code modification. So no more trace locks, no more whatever. So if you're interested in values which flow through your data flow graph, you can say, show me the values right here, and kind of placing a probe there. And by doing so, you don't have to touch any code anymore. And in a even further step, we are going to evaluate that proposal on the effectiveness, and also kind of want to revalidate it with the study we did here with the problems, and see if we really improved here something. Yeah, that's actually already it. Was quite a bit faster than actually I have intended to. Thank you very much for your attention, and I'm happy for any input, any feedback, or any question from you guys. Yeah, thank you.
Thank you.
Thanks.
I think I'm going to have to download like a TV applause track so that I can play it after the talks. So please, if you have any questions, raise your hand. I'm taking a look at the participant list to see if anybody wants to ask anything. Sam, go ahead.
Hi. So you briefly mentioned some ability to like probe a stream to inspect its values. I'm interested in that idea, and can you perhaps elaborate if you've thought about like what particular mechanism that is?
Mm-hmm. Yeah, sure. Thanks for the question. I can give you as kind of a sneak preview to this. I have in my backup slides here. So in this tweet, you kind of see the entry point on this adding a probe to the code. So for the prototype, I'm working in the current iteration on the problem. In this case, Visual Studio Code allows you to add to a particular operator in your data flow a probe. And the IDE, the editor, gives you then kind of an additional pane on the, maybe I can draw in here. Yeah, exactly. You get kind of an empty pane over here, which will in the end show the probe's output. And once you start running your program at runtime, you will get some kind of live telemetry information over here in this probe monitor. So you see stuff like something was subscribed, you see there was a new value, yeah, like this. And by doing so, of course, this looks very much like the usual trace lock, I have to admit, but this will use some more elaborate visualization in the future, hopefully, because yeah, it should give you more ability to live interact with your data flow and maybe see what specific kind of source did emit that particular value, where did it flow through, what kind of operators were involved while this was produced. Does this kind of resolve your question?
Yeah, if I may, I have perhaps a very short follow-up question. Do you suspect that the probe is always at a very concrete location in the code, as in one particular statement, or would you like define a collection of streams that you'd all like to inspect at once? I'm not sure. So the question is, would it make sense to have extra abstractions for it?
So if I get you right, your question is, do you pick from a list of streams, or do you have kind of always the source code as entry point to your list of streams, so to say?
Yeah, so like currently the way you explain this is, I guess, the streaming equivalent of a breakpoint. But I'm like wondering if it makes sense to have support within the language itself to define a certain set of conditions, for example, a bug condition that would be like automatically intercepted or something. I'm just brainstorming.
I see your point, yeah. Yeah, absolutely. That's actually very interesting. My initial start on it was really like the code is your entry point. So you already have started to think about how your stream composition looks like. But I think that's very an interesting kind of break on exception thingy, right? So which brings up this whole machinery here as well.
Yeah. Okay, thank you.
Cool. Thanks for the input. Very interesting.
I have one comment about this, a follow-up question to that one. Sorry about the noise. Yeah, a poster just fell off. So some of the work that we have been doing is also on debugging for streams and functional reactive programming, but also like in the continuous sense, but also in the discrete sense. And essentially the framework that we have for this is that, first of all, everything is fully referentially transparent, meaning fully reproducible, meaning that if you feed the same input to your system, then it's going to get to exactly the same point as the last time. So if you record the input trace to your system and you feed it again, no matter how many times you do it, you restart the program, you feed that, it's going to get you to the same point. Because essentially we structure the system using signal functions instead of streams. So the input from the real world and the actions and the side effects are kind of like external. That means you can always reproduce the state of the machine. And then we have this debugger or kind of tool that allows us to jump to a specific point in the trace. So it kind of records the whole thing, and then you can load it and click on a sample and say, I want to see what was happening here. And then it connects through telnet, it connects to the simulation, and it runs the simulation forward up to that point. And you can go back and forth and change the inputs and change the stream and so on. And so it seems like very, like in some way connected, but it's a different approach, because here, essentially what you have with those observables or with those monitors, so to speak, it's kind of like a side effect. You're essentially saying, I want to add another reactive element, which is based on this thing that I'm looking at. And this reactive element has a manifestation, but if the manifestation is not in the user interface that I'm creating in my program, it is in the debugger, it is in Visual Studio. That's where the side effect of this particular reactive value is being presented. And that's what you're seeing in that trace, which in this case you see, well, pseudo trace. In this case you see vertically, but you would want a graph or something like that. So it seems like we're all doing the same thing, just in slightly different ways. And I wonder, like, here it still feels a bit kind of like you have to go step by step to the point, or like if you want to know, like if you want to reproduce a moment in the simulation, how do you do it? Like, let's say that you try your simulation, you try like feed these inputs and these outputs, click here, do that. How do you get to the same point?
That's an interesting point. The approach so far we took is it's never kind of an art or a recorded simulation. It's always connected to the very running application, let's so say. So it's really the JavaScript runtime environment of the browser or Node.js or whatever. But I think what you are pointing on more is like, is it even necessary to log things if you kind of can predict already by the way your input and side effects work, right?
Well, so here the thing is, the user, like you cannot predict what the user is going to do. So you still have to record something. But what you do is you divide your system in two parts. You have the streams that come from the external world on the one hand, which these are user clicks here and there and so on. And then you have your actual application logic, which is not defined normally as streams, but as functions between streams. So they take the user input and the external world as input streams, they manipulate it, and then they produce output streams, which you render, presumably, or something like that. So that is that strict division where your whole logic is separated from the external world that gives you this reproducibility. And it also gives you the ability to ditch completely the user input and say, no, I pre-recorded the trace. Here you go.
Yeah.
So I guess I'm guilty of it. This is more of a comment than a question.
I mean, the crucial thing in the end, I guess it's not really. I guess it's not really about where. So if I'm following your thoughts correctly, it's not really about where the behavior comes from. Might it be the user or some simulation, right? In the end, we need a common way how to visualize or represent this way how such a flow or a graph works in the end. So yeah. I mean, having the ability to connect to the running thing where someone clicks. I mean, it's for debugging harder anyway. When you debug, you like if stuff, as you said, is reproducible and you can keep running it over and over again. But I think it's still the missing piece, especially for when you work with RxJS, is how can I get a view on my graph, on my system of reactive building blocks, so that I understand it, because this is rather simple, but we all know it grows and it gets usually not simpler.
No, it doesn't. It doesn't. So a thought connected to this, and it's short, is recent work that we did funded by DARPA was on translations from SysML, which is a modeling language, into functional reactive programming. And what we have is we have a graph of blocks with inputs and output ports connected to one another. And there's information flow. And we translate that into like functions between streams. And what we have is kind of like this is a research prototype. It's definitely not production ready. And what we have is this tool, this helper tool that will load this graph, show it on the screen, and then allow you to run it, and then show you the information as it flows. So you can just hover over, like every single component is a box. You can hover over the connection and see how it's changing. So, and it would be pretty trivial to say, instead of showing me the value now, show me the history up to a point, because that leaks memory. But yeah, it seems like it would be, it's similar, except that here, I guess you're debugging over the code, if I understand things correctly, right? With this new direction that you're taking. You're still going to the code and selecting a reactive value and saying, this is what I want to look at. Right?
Yeah, absolutely. I mean, this is let's just say the first problem of many we choose to start working on this. But I can totally, I mean, this, if I could just envision something like you just described, where you can make it more tangible to work with your graph, and even the values within, and go even back and forth in history, maybe. I mean, this is, I think this would be the kind of ultimate, or one way of showing the ultimate vision for such a tooling. Absolutely, yeah.
There's another question. Thank you for answering. There's another question from
Thank you.
Hidehiko.
Yes, thank you. I was about to forget my question. Let me try to remember. So regarding the visualization of trace logs, I think the operating system people are also struggling with the huge number of trace logs and how to visualize them, and they are even developed their own kind of tools, visualization tools, which where I think the point is that in operating system areas, there are multi-threads and the events are related to each other, and also the causality of one event in one thread has a causality of the other event on the other thread. So they try to extract those dependencies and try to visualize them. So I'm wondering that if the trace visualization of trace logging problem in reactive programming is something to do with those kind of visualization problems.
Thank you very much. So especially when you start with the first tutorials for RxJS, they have this kind of thing. They have the marble diagrams. So you really have kind of a timeline, and every value which is emitted throughout the lifetime is a marble on that thing. And so could you elaborate a bit more on what particular thing you're referring to? Because that sounds also interesting, seeing other fields having rather similar or same problems for visualizing that stuff.
One of the system is called CViz. I don't know the correct pronunciation is, but I can give you a URL of the system on the chat. So, and I think they also try to visualize those bubbles in line, and then drawing arrows like this event has precedes to that event, and then they can also do some kind of filtering about using dependencies.
Okay. That sounds cool. I will have a look into this. Thank you very much for the input. Nice. Always interesting. Cool.
I think we have time for one more question. Bjarno, and Guido also has one question.
So my question, my question is about the different types of errors that you can encounter in stream-based programs. So I think there are multiple types of errors that you can have. For example, types about how the signals or streams in your case are being composed. And the other type of error is like the code inside that, for example, in a map of a signal or a stream, whatever. So my question is, how can your debugger help to differentiate between these two kinds of errors?
So could you just repeat quickly that I didn't got it right from the start, the two types you just described of errors?
So either, I think one type of error is an error in the way how the program is composed. You have two streams, you want to merge them, but maybe the merge operation is not the right operation that you need to use. And the other type of error is like the functions inside a map, a flat map or other type.
I got your point. Okay, thank you very much. So I think the first case you kind of mentioned, this is really was one of the key bugs we added to the problems we showed during the observational study. So there is this thing called switch map and flat map in RxJS, and one really unsubscribes from the previous observable, and the next one just keeps it subscribed. So you kind of get double emitting values afterwards. And if I got you right, this was kind of the first part of error as you have described it. And so there are in particular runtime, or no, not runtime events, lifecycle events to an observable in RxJS. So you see when something is subscribed and unsubscribed. And I feel like this kind of error can rather good be brought to the surface by exposing this kind of thing in a good way in a visualization, like really seeing there is a new observable created over and over again, maybe over time. The second part inside of a lambda function or a fat arrow function in JavaScript, yeah, I think maybe this is then more part again for the traditional debugger, I feel like, because that's really imperative code in the end. Yeah, so does that answer your question?
A little bit. I think my question is more like, how do you integrate, if you have these two debuggers, how do you integrate both of them? Because you might want to step through the arrow function in JavaScript, but once you step out, I mean, where does that value flow to? This is information that you also need in your debugger.
I think that is one of the key things to solve in regards of the developer experience I mentioned in my talk. That's really something we want to nail down so that it feels like one thing and not two things disconnected to each other. But that's something yet to solve, absolutely.
So I think Guido had a question.
Yeah, it's a very, very quick one. So how much of your work is, let's say, Rx related, and how much can be generalized after all? I think, I mean, you could take a different angle, and then also from a research point of view benefit, saying, you know, this is more general than this library. This what do you think?
So the basic architecture which is there from the proof of concept, I think, is not really tied to having only RxJS backends, so to say. So once you have this kind of protocol between the RP in runtime environment and your debugging tooling running, so that each can talk to each other, this should not be tied to a specific runtime environment in the end.
And just, is the question answered? Like, did I interrupt? Okay.
For my part,
It seems like it was, but I didn't mean to. Just, I don't know if you're familiar with the work of Brett Victor. So essentially, he was a designer and a programmer with Apple, and then many other companies. And he did work, gave a talk at some point. I think it was called, if I'm not mistaken, Inventing on Principle. And it was about debugging applications in JavaScript. And essentially, he had this way of running a game up to a particular point and then going to the left of the screen where he had the code, where the simulation was on the right, modifying values and looking at the values of variables at that point and so on, and then continuing the simulation from that point. So it's kind of like, it was kind of like a dynamically evaluated environment for JavaScript coding. And it seemed like another interesting take on being able to look at the state of a variable at a particular point in a more reactive way. It wasn't specific to reactive programming. It was more about just imperative programming or object-oriented traditional programming in JavaScript. But it seems like the ideas were connected. And it's just for fun, it's an extremely cool time to watch. So,
what was the name again?
Brett Victor. I will write it in the
Oh,
chat.
yeah, of course. Yeah, I know that one.
He's
I know that
like
one.
beyond this earth. He's amazing. Yeah.
Cool, thanks. Oh yeah, of course. Yeah. Very, very cool portfolio page with nice interaction. Yep.
All right. Well, thank you once again for the talk.
Thank you very much.
And yeah, let's go on with our next speaker. Who will be presented? Is it you, Tetsuo?
Yes.
Perfect. Well, without any further delay, I would like to introduce Tetsuo Kamina, who is going to be talking about managing persistent signals using signal classes.
Okay, thank you very much. Can you see my slide? Okay.
Yes.
Yes. So my name is Tetsuo Kamina from Oita University. And this is a joint work with Tomoyuki and Hidehiko regarding management of persistent signals by using our new language construct, signal classes. So I think most of the audiences in this workshop are familiar with signals that are also known as time-varying values. So let me introduce our language, Signal J, that is an extension of Java that supports signals. So here is an example of interactions between sensors and actuators that is written in Signal J. And in Signal J, a signal is declared using a modifier signal. And so here's a signal position that stores the current value of the sensors. And here's another signal, power difference, that stores the power difference of the motors that is calculated by the PID control method. And so the signal power difference depends on the signal position. And so any changes in position are propagated to power difference. And in Signal J, we can imperatively update the value of position, and the value of the power difference is always automatically updated. And sometimes we want to handle the past values of some signals. But this handling is likely discouraged in many reactive languages because using the arbitrary past value leads to the problem of time leak. But actually, the past values are useful. So, for example, I would like to introduce another example of the vehicle tracking system that is written in using signals. So in this example, the signals are used to represent the current position of the running vehicle and its velocity. And in this example, all the signals past values directly corresponds to the travel records of the running vehicle. So those the past values of those signals are useful to inspect the record of dangerous driving signs, such as the sudden braking and start. And those signals are also applied to replay the driver's behavior. So for this purpose, we had proposed a concept of persistent signals that are time varying values with their execution histories. So a persistent signal is declared using a modifier persistent, and the language processor maps each persistent signal into the underlying database table that stores all the past values of the signal as a time series data. And this mechanism is implemented using a RDB-based time series database that is called timescale DB, and it provides a generalized way of time link management by leaving this management to the underlying database system. And in this mechanism, the dependencies between signals are implemented using the RDB views. So in the vehicle tracking example, so assuming that X coordinate and Y coordinates of the vehicle are synchronously updated, the velocity of the vehicle is calculated implemented using views of the RDB database. So for this purpose, we provided a set of view creating API method that is prepared in advance. And so each method corresponds to the corresponding view creating SQL statement. So in this persistent signal network, the source of the network is implemented using the tables, while the other signals that depends on the sources is implemented using the views. And we call such a signal as a view signal, so its history is implemented using the views that are created by each view creating API method. But there are significant problems in the persistent signals. First, persistent signal cannot represent the complex data structures. So, for example, in the vehicle tracking example, we need to declare the persistent signals for each X and Y coordinate. And second, it is the programmer's responsibility to synchronize those X and Y coordinates. So this synchronization is explicitly performed. And finally, in the persistent signals, the database tables are created at compile time. So we cannot create the persistent signals dynamically. And this means that we cannot add the new vehicles at runtime. And we also, moreover, we cannot change the structure of persistent signal network at runtime. So to tackle these problems, we propose a new language mechanism of signal classes. A signal class is a class that packages all the related persistent signals. So we can declare a signal class vehicle that contains all the related persistent signals that represent the property of the running vehicle. So we can represent the represent the X and Y coordinate of the vehicle as well as the velocity, and those are all those features are declared using the persistent signal, and those are packaged into the one single class. So it is considered a compound of the persistent signals, and each signal class can be instantiated by explicitly provide an unique identifier. And so this instance forms a unit of synchronization and a unit of life cycle management. So this instance can be considered a small world where all the persistent signals inside it is synchronized and follows the same life cycle. And here is the life cycle model of the each persistent signal class instance. And the life cycle is managed for each signal class instance that is provided with the unique identifier. And this state machine diagram indicates that the database table and related views are created using the fresh ID that is provided to the signal class instance when this instance is firstly created. And then we can send some messages to update the status of the signal class instance. And eventually the application may stop, but the signal class instance exists on the disk even after the application stops. And this instance resumes with the previous state. So when the application restarts, so the status of the signal class instance is preserved until when we explicitly destroy this instance. And this management of the lifecycle is performed using the interface for the lifecycle management that is implicitly implemented in all the signal class instance. So for example, we can use the set method to update all the persistent signals that are declared using within the signal class instance. So this set method implements the synchronized update. So a signal class instance is implemented by underlying database table and some related views. And the database table consists of the columns for each persistent signal. And also it has columns that corresponds to the signal that calculated by those persistent signals, but not using the view creating API method. So the set method first calculate these signals by using the provided arguments, then insert the new row to the table by choosing the current timestamp. And on the other hand, the values of the views are calculated by the underlying database system on demand manner. And in this mechanism, we can also declare the signal of signals. And as in the previous work, the persistent signals only support the primitive types that is supported by the underlying database system. But in signal classes, there's one exception. That is, we can declare a signal of signal class instances. So we can use the name of signal class as a type of the persistent signal. So we can declare a signal class monitor that monitors the running vehicle, and we can, switch the running vehicle at runtime. And in this running vehicle, there are this vehicle also has the network of the persistent signals. So this is like a dynamic switching of the persistent signal networks. So we have shown that all the problems of the persistent signals are tackled by the simple idea of signal classes. So we can, we can declare the compound of the persistent signals, and we can instantiate the signal class dynamically, and within the signal class instance, all the related persistent signals are implicitly synchronized. So I would like to go further on more technical details that are not shown in the paper. That is the formalization of the this mechanism. So we are currently formalizing the specification of the signal class mechanism, and the syntax is provided in a featherweight Java-like manner. So the signal class has declarations of persistent and view signals, and also the method declarations. And a persistent signal is declared as a field by using the modifiers persistent and signal. And the view signal is also declared as a field where the right-hand side is a call of the view creating method. And if the right-hand side is not a call of the view creating method, it is not a view signal. And a method just returns an expression. An expression can be either a variable or an access to persistent or view signal, an update of the signal class instance, an update of the and the call of the method, and an instance creation. And in this calculus, every instance has an execution history that is a set of RDB relations. And this instance is also provided with a unique identifier. And in this calculus, every value is an element of a set of identifiers. And in this calculus, every type is a class, and every class is a signal class. And every field is a persistent or a view signal. And I would like to explain how the execution history is represented using the set of RDB relations. And each instance has a set of RDB relations that consists of a table PT and the set of views. And a table PT consists of the attribute for the timestamps and other attributes that correspond to the persistent signals. And view consists of the timestamp and its values. That value is computed by the view creating function that is provided in advance. And we assume that the persistent signal corresponds to, every persistent signal corresponds to the corresponding attribute in the table PT. And we assume that the view signal corresponds to the corresponding view in the set of RDB relations. And we summarize the semantics of the calculus. So the computation rules are provided for each form of the expressions. And in this computation, we assume that environment sigma that maps the identifier to the corresponding instance. And the access to the persistent signal results in the latest value of the corresponding attribute in the table PT. So this is specified using the relational algebra that selects the table of the latest time and projection by the attribute P. And similarly, an access to the view signal results in the latest value of the corresponding view. And an instance creation just as the fresh identifier, the mapping from the fresh identifier to the created instance to the environment sigma. And the semantics of set is a bit complicated. It updates the environment sigma by replacing the table PT with the arguments V bar and non-view signal values W bar that are calculated at the same time. So each value W is obtained by evaluating the corresponding expression that is from the right-hand side of the corresponding signal declaration. And this evaluation is performed in a big step manner where the time doesn't proceed. And so we chose a new timestamp to form the tuple. And using this new tuple, the table PT is updated, and the environment sigma is updated by this new PT. Oops. And this is still ongoing work. So there are some other considerations. So specifically, the previous set semantics only just synchronize only one single signal class instance, but sometimes we also want to synchronize with other signal class instances. So for this purpose, explicitly using the global time might be an easier solution. And this, anyway, our goal is to provide a proof of the some kind of important properties, including glitch freedom. So now I would like to explain how this mechanism is implemented. The implementation consists of two parts, a compiler and a runtime library. The compiler is implemented using extend.j. So this compiler translates the signal.j program into the Java program. And each signal class implicitly implements the signal class instance interface that is for the lifecycle management. And so the compiler implicitly inserts this instance into the each signal class. And the runtime library implements the behavior of signals such as the update propagation and access to the underlying database system and synchronization and so on. And here the runtime architecture of this implementation. So an instance of the signal class is each signal class instance implements the signal class instance interface that provides the interface for the lifecycle management. And each signal class instance also contains the objects that represent the persistent and view signals, and all of them implement the persistent signal interface that is also provided by the runtime library. And each object has a mapping from the time series columns to its corresponding field. And each table, the name of the table is determined by the identifier provided by each signal class instance. And similarly, every view, the name of the view is determined by the identifier and the name of the view signal. So there are some related work. So as our proposal is about language design supporting signals, so there are apparent connections between our work with the other existing reactive and functional reactive languages, and among them, the imperative update of signals are also supported by the reactive language RESCAL. But the persistent signals are only supported by the signal J. And we also consider that our work is somewhat similar to the time travel debugging that uses the signal update histories for the debugging. So it enables the rewind and replay of the program execution for debugging. Examples are Elm debugger and reactive inspector that is a debugger for the RESCAR. But those debuggers do not support the lifecycle management and query API mechanism. So in conclusion, we have proposed the signal classes that tackles all the problems of the persistent signals. So each signal class supports the compound of the persistent signals, and each signal class instance provides the unit of the lifecycle management and synchronization, and it enables the dynamic switching of the persistent signal networks. And our future work is to finish the formalization and to provide proofs of some important properties, including glitch filter. So this is the end of my talk. So thank you very much. And any questions?
Thank you for the talk. So yeah, we have a bit of time for questions. I don't know if anybody, I don't see any hands up, but please, if you have questions, just raise your hand. I do have one question.
Yes.
So as far as I understood, the way that you connect to your database is essentially that you have to name the signal. You have to give the signal a full, like a persistent name, right?
Yes.
So technically, you could get the name wrong and say, in my last version of the program, this signal was an integer, for example. And I run it again, but now I treated this integer as a floating point number or as a string. And then I would get a type error, I guess, right?
Mm-hmm.
Or does it just cast and not warn you? What would happen then?
Yes, thank you. So well, currently we are working on the so I think this is a part of some kind of the database migration. We actually provide some mechanism of the database migration in the previous work. I'm not sure this is complete, but there's some mechanism of the database migration. But in here, the things might be becomes complicated because the database tables are now created at runtime, and but the structure of the database is not so how can I say not very different from the previous work. So the answer is currently we do not have answer for the how the migration is performed, but we are considering So the no.
Yep. Mm-hmm.
Yes, we are considering about this. I have yes, we are currently working on this issue.
Mm-hmm. Okay, thanks. Wolf, you have your hand up.
Yeah, hello. Thanks for the presentation. But maybe I missed it completely, but I don't understand why you need the set in your language, because I would expect if you have a monitor that has a reference to a vehicle and the vehicle has an X and a Y, I presume that these are GPS coordinates. So if we are in a reactive language, I understand that if the X and the Y, they change reactively, the vehicle change. So doesn't the monitor automatically change? Do I need to, I don't understand why you need set in the language. So I would expect if you have nested data structure and there is like an outer data structure referring to an inner data structure, in a reactive language, if the inner data structure changes, then the outer data structure automatically has to change. So why do I still need set?
So in our language, the source of the network is, we assume that the source of the signal network is updated imperatively. So all these other signals are automatically updated, but the source of the network is imperatively updated. So, but we want to those X and Y coordinates. So, but in this example, we want to assume that, which slide? Yeah, here we want to assume that all these states are synchronized. So for this purpose, yes, we just so we to synchronize this this source.
Is this because
yes?
Is this because you are emulating the outside world with sets all the time? So, but in the real language, if you can connect the X and the Y to some GPS coordinate, which is automatically there, then you don't need sets. Is that correct?
Yes. So so how can I say so the connection to the Jeep so if we consider the the some library that connects communicate with the outside of the language. So yes, the things might be easier, but so at some low level, we still need to this kind of state mechanism. So this is provided to connect the implement a connection between the from the outside world. Did I answer your question?
Yes, I understand why set is there at the very lowest level, but I would expect when I use the language and I somehow have this X and Y GPS streams that are there, that I can just plug your vehicle to this X and Y stream, and that automatically under the hood, the runtime calls set all the time. So I don't think that I need set in my language or in your language.
Yeah. Thank you.
Okay. Yeah, thank you.
All right, thank you very much. So if there's no more questions, I would like to thank you again for your talk. And we have a break now for 40 minutes. The next session will be at 12 o'clock here, which is, I think, 6 o'clock in Central Europe. So see you in a bit. Hello, everybody. Hello, Mark.
Hello.
How are you? Thanks for coming.
Doing well, thank you.
Let me make you a co-host, just in case you need to do anything during the meeting. There you are.
Thank you.
So we're supposed to start in about 3 minutes or so. You weren't in the last session, were you?
No, I wasn't able to.
Mm-hmm. So there were, I don't know how many people will get in this session, but I think there were 13 or 17. It was going up and down because we had a few connectivity problems, but around those numbers. So maybe, yeah, I don't know if we want to wait too much, but.
Sure.
You're the boss now, so.
All right. Well, we'll give it at least 3 minutes then.
All right.
And Tian Zhao, is your mic working? Is everything working for you?
Can you hear me?
Yes, definitely. Yep.
Okay, good.
I'm just gonna put that up in case somebody pops in now, so that they know where they are.
Great. And everyone has, it seems like everyone has screen sharing permissions, so Tian will be able to do that.
I think so, yeah. So you can just take over whenever you want. But if you can't, I'm here. So.
Great. Okay, it's now noon Eastern time, New York time, and we're going to get started with session 2 of the Rebels workshop. Welcome all, and thank you for coming. So we're going to have 2 talks during this session, and the first talk will be given by Tian Zhao, and he will be presenting his paper Asynchronous Monad for Reactive IoT Programming. And with that, I'll ask Tian to unmute and share your screen for the slides, and you can take it from here.
Okay, so let's see. Okay, are you able to see my screen?
Yes, we are.
Okay, all right. My name is Tian Zhao. Today I'm going to give a talk on our experience with developing a library for IoT programming using asynchronous monad. The outline of this talk is that I will first go over the characteristics of IoT programming and what kind of features we would like an IoT library to provide, and then talk about the main abstractions we defined for this library, which include AsyncM, which is abstraction for composing asynchronous computation so that it is cancelable, and push-based data stream, and a pull-based signal. And then I'll talk about the push-pull based design for IoT application. So what is IoT programming? So there are a lot of different applications involve IoT programming. For us, the motivation is based on a project we're working on with industrial partners to monitor industrial devices such as electronic inverter, PV arrays, generators, and wind turbines. We want to capture those sensor data continuously and calculate key performance indicators or KPIs. So those KPIs are used to monitor the health of those devices as well as their performance. We would like to store the data and the KPIs in database after they are calculated and display the data in real-time charts, and also control what kind of device to monitor, what kind of KPI to calculate through user dashboard. So we have a number of devices. Every device has possibly several signals, such as current and voltage. Those are captured and sent in batches, so network, excuse me, then go into an IoT analytics system, then go database and for visualization. The computational characteristics of IoT is that some of the data signals are from electronic devices that are higher frequency, such as 10 kilohertz or more. And some of the KPIs are computational intensive, while others are not so much. For example, to calculate the efficiency of a solar array, it's just a simple division between the array power and the sun power. But for KPIs like total harmonic distortion, which measures the quality of electric signal, we have to take moving windows of voltage or current signal and apply Fourier transform to each window and then find out different harmonics and perform the calculation for the THD. So those calculations proceed in real time. However, the bandwidth of network and the load of the CPU that those computation is running on may change during the course of the execution. So we cannot preset a certain data sampling rate for those sensors. And if it's too high, then we can potentially lose data, or the latency gradually getting larger and larger, or just have a buffer overflow. So to avoid this problem, we need to monitor the performance of the computation in real time and make dynamic adjustments. So because of these problems, for a library for IoT programming, we would like to have certain kind of features, such as asynchronous handling of the data and the control events, because the sensor data arrives asynchronously. And we would like to have imperative sharing of streams to avoid duplicated computation. And we'd like to continuously monitor the streams and also cancel streams that are no longer used. Also, the computation for KPIs needs to be synchronous, so that if we take, for example, the voltage and current of inverter to calculate the power, those data signals has to match by their sampling time, so there shouldn't be any glitch. Finally, the implementation should be, the design should be portable to dynamic languages using event loops, because in our experience, a lot of hardware or simulation tools only has interface using some of the language like Python. All right, so here's the main abstraction we defined for our library. So I'm going to present the design in Haskell, even though implementation in another language like JavaScript is it's almost the same. It just does not have the nice syntax. So the first abstraction is async-m. We define async-m to represent composable and cancelable asynchronous computation. Async-m is basically a function that takes a progress value and continuation and wait for the asynchronous computation to complete and then pass the result to the continuation. The progress value is simply a list of mvars. Each mvar represents a cancellation token. So if you set it, that means it's canceled. Otherwise, it's still alive. We define a stream type to represent asynchronous events pushed by a producer. The stream is essentially a sequence of asynchronous async-m. The stream is essentially a sequence of values wrapped in the async-m. So the stream actually can terminate. In the paper, I did not include that case, but in the implementation, having an end case, it makes it simpler. And then the third abstraction is signal. This name is a little bit unfortunate. It is not the same as the usual FRP signal we understood. I really mean it by signal, I really mean this IoT data signal. So signal represents synchronous values that can be pulled by a consumer. It's just some data that's stored in a buffer. We can continuously ask for more data. And based on the signal type, we have two derived types. One is an event, which is a pair of the sample period d time with a value, and the behavior on the other hand is it's a signal that can give sample time and return a value. So the behavior abstraction allows us to resample the data value using any delta time. So let me give you an overview of what async-m does. So async-m, like I said, it's basically a function that takes a progress value, run an asynchronous computation m, and passes result to the continuation k. So if I want to raise two async-m, m1, m2, we can use a function nem that allocates a new cancellation token p prime and add it on the existing progress list and run the two asynchronous computation m1, m2 in parallel. So if m1, say, completes first, it checks whether the progress is still alive. If it is still alive, then cancel p prime and continue with the result. And then when m2 completes, since p prime is already canceled, the computation will stop. So this is nothing new here, but this design does help in the sense that we can implement this without any threat for racing. As an example for this use of async-m, let's say we have a program. We want to download a file using a list of URLs. And each download attempt will wait for 2 seconds. If the download fails to complete in 2 seconds, we're going to try the next URL in the list. And we also want to stop the entire process if you cannot download any file after 5 seconds. So we implement this using NEM that raise this call to the download with a list of URLs with the timeout, 5-second timeout. So this will allocate a cancellation token P. And then when we start the download attempt using the list, we raise the call to the HTTP function with the 2-second timeout. So if the HTTP call completes before the 2-second timeout is up, result is saved into the path. And it not only wins a race against the 2-second timeout, but also against the 5-second timeout. The entire program will stop there. Otherwise, if the 2-second timeout is up, you will abandon the current attempt and continue to loop back and try the next one in the list. Of course, if the 5-second timeout is up first, then the entire thing, entire call to download will be canceled. So this is achievable because the progress value used by the download function include this token P that was allocated when we do the outer race. Okay, so with that construct, we can define a push-based stream to handle asynchronous events, such as the IoT data that was sent over network. So a push stream can be made by repeating an asynchronous computation, async_m, indefinitely. So here's a function repeat as, take an async_m value as input and return a stream. Because async_m needs time to run, so the stream will start with nothing value. And then we run the async_m and wait for its result. Its result come back. If it's still alive, we'll continue and loop back, try it again. We can also run a stream by using a run function that take a stream and a side effecting function f and run the stream for each value. So the output of running a stream is also an async_m. So this allows to compose the execution of a stream as an async_m value. So to start with, when we run this, we also check if the progress is alive. If it is, we pass the result of the stream value to the function f. Then we wait for the future value of the stream. If it's still alive, we do the same thing again. Now, of course, if at some point the progress is canceled, then the running of the stream will be canceled as well. Our push-based stream has a monadic interface. So its bind function is implemented by calling a join function to join a stream of stream. So let's say if I have a stream of streams, S1, S2, S3, etc. The way we join a stream is to take the first stream, look at its value. The first value, X1, will be returned immediately. And then we raise the second value of the first stream, X2, with the second, the future stream, S2. So both of them are async m values. You can use any m to raise them. And now here, for the future stream S2, we cannot raise it directly. Instead, we have to spawn it to make a copy of it, which essentially just to create a memory location, wait for its future result. Doing this is because if we don't make a copy of it, every time we do a join, S2 will start again, and there could be a problem. So if X2 wins the race, then we'll just return its result and continue with the stream S1. So now X2 will be the head value of the joined stream, and we continue the race of the next value, X3, with S2. If on the other hand, if the second stream, S2, wins the race, then the S1 is abandoned. We'll just join the rest of the stream. So this is the implementation of the join. So it's also, as you see, it's implemented using async as well. We can use thread for this, or we can implement this in a single-threaded language as well. All right, so now I show the relationship between the push-based stream, pull-based signal, event, and behavior. A stream can be converted to a pull-based signal using a function. I call it push to pull. So this function essentially uses a buffer to do this. And a signal can be converted back, by using a reactivate function to turn it back to a stream by drive it with a clock. And if we pair a signal with the data sampling time, then they become event signals, which just the delta time and the value pairs. And with that, we can use a stepper function to convert it back to a behavior signal, which can be resampled using any sampling period. And finally, the behavior signal can be reactivated into a stream by driving it with a clock. So all these abstractions are used to implement a push-pull-based design for IoT data handling. So here's an example of calculating KPIs on on asynchronous data. So let's say I have two push-based streams, S1, S2. They accept asynchronous data packets from the source. So the data arrives in the time that is not predictable, but the KPI calculation needs to match the data samples by their sampling time. So the way to do this is to use buffer. We can convert a push-based stream to a pull-based signal using a channel buffer. So each event of the push stream is right into one end of the channel, while the signal will just pull data from the other end. So S1, calling push to pull S1, we get this signal G1. And similarly, we convert the second stream into another signal, G2. And then we can use the applicative interface of the signal to apply some KPI function F to this and obtain a signal. So the variable A here is in fact have this async M signal type. So we cannot use it directly, but we can lift it using a lift function to turn into a stream that contains just a single signal. Then we use a bind to extract the signal within it and call it KPI. And then we can reactivate this KPI signal with a delta dt time to turn into a stream that will yield an event at dt number of milliseconds. All right, so this is basically the conversion of the signal back to a stream. So this approach allows us to avoid worrying about glitches. The timing of the signal data will always be consistent as long as they're driven by the same clock. Okay, so the other issue we worried about is to avoid recomputation. We really don't want to, because this is functional, and any instance of a stream, if you use it more than once, it will cause the stream to be recomputed. So to avoid recomputation, we use a simple mechanism. We call it the multicast. So the multicast will turn a stream into a shareable stream. So let's say if I have a push stream that take some events, to share it, I will emit its data into an emitter. So the emitter is it's a very simple construct that just contains one memory location to hold one event. and then you return a shareable stream, S prime, that every time you use it, you will start to listen on this emitter when new events. So, so this S prime is used in two places. In one place, we use it to save to the database. The other one is to convert it to a signal for KPI calculation. So to go to two branches, the second branch is supposed to go to the database. But this whole program is supposed to return one stream, and so we cannot return this part. Instead, we just run it. We just run this S prime using the run S function to save the database for its side effect. And now this run S return async m. If I just lift it into a single stream and as is, the program actually will wait until this finishes before you do anything else. So that's not good. So what we avoid waiting for it to finish by calling a function forcam. Forcam is it's a really simple function. Just basically run this without waiting for the result. So then this will just start immediately. We don't have to wait for it to finish. And then we can call push to pull to convert S prime into a stream and then do the KPI calculation. And then the result again is converted back to a stream. We can use it for further purpose. Another issue we worry about is to retrieve data from a gateway that stores the sensor data. So in our experience, the IoT data from the sensors are usually sent to some type of intermediate storage. We call it gateway, and then we will pull data from the gateway periodically as much as we need. But gateway does have finite storage, so it cannot store too much data. So we need to pull data from it in a regular interval and consume at the speed that is approximately real time. So we cannot make a data request and finish processing and ask for it again because that would be too slow. So to reduce the latency, we will set up a stream of requests. We basically send requests at regular interval to a data source and ask for data. And then we'll spawn an async m that represent a copy of the request, a copy of the response to the request, and then put into a channel and then wait for its return. So to do this, we first allocate a channel to hold the response, future response. And then, like I said, we for each request in the request stream, we spawn a copy of it and write the copy into the channel. And then we call the run function to run it right away and call fork, so we don't have to wait. So this will start independently. And then we use repeat function to repeatedly reading the response from the channel. The join here will forces us to wait for the result. So once the result comes in, this will return and we'll wait for the next result. So ideally, if the data source can provide data as fast as we request them, this will work perfectly fine. However, sometimes if the network getting slower, the number of requests we send may exceed the number of responses we receive. In that case, the channel will actually become full, causes losing data. So to avoid the problem, we can define a function to dynamically adjust the amount of data we request. So on the previous slide, the request does not specify what is the data sampling rate. We can request data of 50,000 kilohertz, 50 kilohertz, or even 5 kilohertz. So So without specifying that, we just take whatever data the server provide. But in fact, we can actually reduce the data sampling rate if the network couldn't handle it. So let's say we have a function, request fun, that can be used to make a request, a stream of requests, by giving it a sampling time dt. So we can use dt to adjust how high or how low the sampling rate of the data would be. And we can define a function control as allow us to make continuous requests, wait for its response. But then the data sampling rate can be dynamically adjusted based on the speed of the network. So we implement this by recursively construct a stream of responses using join. Essentially, we build a stream of response streams. To monitor the request and response stream, we have to multicast them. So when we call the request function, we get a request stream, but multicast it, and so that return a copy of the request that is shareable, same with response. At the same time, we also return the progress value of the multicast stream, so we can cancel it later. So we monitor the number of responses, number of requests sent for a given duration, and say maybe 10 seconds. And then we wait for all of them to return using this function OM. And once it returns, we compare to see are they the same. If they're the same, we just continue as if nothing happened. If they're different, we can cancel the streams and make a call to this adjust function, which give us a new sampling period and start the whole process again. So this design allows us to balance the speed of request and response, so to sustain the real-time computation. Okay, so finally, the overall picture of what we like to accomplish can be shown on this slide. So this is illustration of a part of the computation we would like to do. So let's say we have a voltage and current data from two sensors. We capture data for voltage and the current, and we'd like to compute the total harmonic distortion as well as the power, because we're interested in the THD at different power rating, because when a system ramps up at low power, the THD tends to be higher, and that is supposed to be the case. But the power should the THD level should go down if the power is higher. So the first process is to capture the voltage as needed, and then we calculate the THD of the sensor current. And to calculate THD of sensor current, we have to multicast to share it, we also use these current and voltage behavior to calculate the power. And finally, the two things can be combined together and reactivated into a stream. We did so the whole thing is implemented Haskell, but we do expect want to implement a real evaluate the overhead of this implementation in Haskell. We use the 128 data streams, convert them to behavior, and then do some simple combination, and then reactivate into a stream of data batches. We test the memory overhead. It's approximately linear to the number of data streams. And the whole thing runs in a single thread on a laptop CPU, and with 128 streams, the overhead of CPU is decent. So in summary, we have defined a reactive framework for handling IoT computation that allow us to perform certain computation asynchronously and KPI calculation synchronously. We have a version in JavaScript that basically mirrors implementation in Haskell. The implementation is relatively straightforward. All we need to do really is, for example, for async is to replace the callback continuation with a promise. But in dynamic language, lack of type system and dual notation does make things a little bit harder. So that's my presentation, and thank you for listening. Welcome any question.
Thank you, Tian. With that, we will take any questions, and I'll invite anyone who has a question, as well as Tian, now that we're not sharing your screen. If you would like to show your video, you're welcome to, but of course you don't have to.
Oh, I'm not sharing my screen anymore?
Oh, no, you are sharing your screen, but if you'd like to share your video while you're asking questions, you're welcome to, but you don't have to.
Okay.
So if anyone has a question, feel free to go ahead. Or you can put it in the chat.
I do have a question.
Please.
So if you go to your, I think it's one of your first slides where you define your streams and your signal. I think you are familiar with the work on monadic stream functions and monadic streams, right?
Yeah.
Okay. So it seems like it's very similar in some respects. And I wonder, I have two questions, I guess. So is async M some variation of a continuation monad?
It is. It is. In fact, that's how we have implemented. We use monadic transformers. So it's just a stack of continuation monad, IO with at the bottom, and the reader monad.
Yes.
We do have exception monad as well for exception handling for async M. But the implementation, every instance of is derived.
So then what is the benefit of having your own framework instead of using something like that already exists? Did you find any limitations or anything you couldn't do just by building it on top of?
Are you talking about a framework like RxJS or
no, like Dunai,
function?
which is an implementation?
Dunai. Oh, I see. Yeah, right. So so I look at Dunai, and I probably had some misunderstanding of it, but I just saw an arrow interface, and I used arrow interface before. I just find it harder to use in a dynamic language setting.
But you don't have to use it. Like the arrow interface in Dunai is completely optional, but you don't have to use it at all.
Oh, I see.
So, for example, the definition of signal that you have there at the bottom is exactly the definition of a monadic stream.
Oh, yes,
and
yes,
you
yes,
can
it
use the
is.
same applicative interface that you're using.
Yes, 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 it is. This part, the signal part, is not any different. It's just a stream itself. I want to be able to cancel it. That's the main thing.
So you can, yes.
I want to be able to cancel it, and so the cancellation flags are just it's convenient to put this in any settings, and as long as I have a handle to the progress value, or I can just raise it, it will be automatically canceled.
So
the cancellation you can also add by adding, for example, maybe monad to the stack. And that's maybe it's a bit overkill to use monad transformers for all that, but in principle, having a cancellation is. I'm not sure whether cancellation is a thing in its own right, or whether, but rather I believe it's just yet another monad in the stack. Morally,
not sure about that. So this is really imperative. So the MVAR is a mutable variable, right? So Oftentimes I encounter the fact
that's
that
right.
to keep something running. When I say for, really it just allow a stream to execute on its own, and I lose handle to it otherwise. The only way I can cancel it is to use this the progress, the cancellation token that's passed in, and the cancellation token, it will thread entire program, and it can be nested again longer, of course. So a stream, if I run it, it becomes async, and then async become part of another stream. And the signal also can be reactivated into a stream. So because everything can eventually turn into async, I can cancel it at any moment. But of course, this is a cooperative cancellation. It's not really, it's not a thread based. So you don't kill it. So you have to wait until you reach a checkpoint when it checks liveness to see if the progress is canceled or not. If it is, then we'll stop executing. So that's one of the main motivation here.
Thank you, Tian. So we have 3 more minutes for questions. We've got another question from Manuel Alabor. Apologies if I butchered that.
That was quite all right. Thank you. I have a question regarding the migration or transformation to JavaScript. Were there any specific challenges or pitfalls you faced, or was this rather straightforward?
Mostly straightforward. In fact, I did the translation in one afternoon.
Okay.
One of the problem with Java, one of the problem with JavaScript is that the lack of type system really drive me crazy, because I would like to use TypeScript for this. Hopefully, we'll handle some of the problems. But for the direct translation to JavaScript, I couldn't debug it unless I tried in Haskell first. So that could pose a challenge. Yeah.
Okay.
But otherwise, the construct are mostly the same. But there's some problem, like overloading is a problem. So I've defined a lot of methods for classes. It's not a direct one-to-one, but it's close enough. I even made classes just represent maybe.
Maybe something interesting you might look like into is, of course, TypeScript is rather closer to JavaScript itself, but there are things like PureScript, for example, which is much closer to Haskell. Maybe could give you some help with translating it over.
Yeah, I completely agree with. But I'm not sure. PureScript. Okay, so my understanding PureScript is extremely limited. Runs the what is its concurrency model is unclear to me. So of course I also worry about performance. So when I implement async in JavaScript, all I need to do is to turn this part into a promise, and the promise does bring a lot of benefit in terms of composing. So I can treat, for example, I can treat the signal as a generator in JavaScript, and that makes things a whole lot easier. So a lot of implementation involve synchronous computation, doing KPI calculations. I can just treat them as generators to mix together. That's kind of nice that way. Yeah, debugging is harder though.
All right, thank you, Tian. We're unfortunately out of time for questions, but that was a really great talk. Just like to give you a round of applause one more time.
Thank you very much.
Can I ask a quick question and cut off 1 minute of my talk?
Oh, sure. Go if it's your own talk.
Can you replace the I/O there and do something like a poor man's concurrency? There's an old paper by Kuhn Klassen, where basically instead of having M bars and then I/O to manipulate the M bars, represent the state of the M bars algebraically in the continuation parameter in there. You think something like this might be possible?
Yeah.
Maybe it's less efficient, but it might be interesting for testing because it's reproducible then.
Yeah, that's definitely something to consider. Actually, I looked at the paper you mentioned, but the one thing that I couldn't deal with is really reproducible events is hard to come by, especially when I do testing. So I'm not sure. I thought about it. I just didn't think it's possible at the time I was looking at that paper, but I really forgot why. Sorry about that.
Okay. Yeah. Well, it's a non-trivial question, definitely, but we can chat about that later, possibly. Okay. Thanks.
All right. Thank you. Thank you.
Wonderful. Yeah, lots of really great questions. I have my own questions too, but I'll have to save them to follow up via email. All right. So with that, I'll ask Tian to end sharing your screen, and we will move on to the next talk of the session by Manuel Behrens. Again, apologize if I haven't got the pronunciation right there. With his paper, The Essence of Live Coding, Change the Program, Keep the State.
Hi. So can you see my presentation and hear me all right?
Yes.
Awesome. Okay, so this talk is about what I call the essence of live coding in Haskell. It's a bit provocative title, but bear with me for a minute with that. The motto for this is change the program, keep the state. So what is all this about? Basically, I have a live coding framework, which is still in the prototype phase. You can definitely use it. I would maybe not yet write a web server with it that goes into production, but you can use it for a lot of things already. And what I want to do is capture the essential idea how to do live coding in a statically compiled language. And it's a general idea, so you can use it for a lot of, you can apply it in a lot of fields. You could use it for audio programming. In fact, I have used it for all of these three that I'm listing here: for audio, for video, for video programming, write a web server. You could also have a web front end written in it, and all sorts of other things that I haven't thought about even. And it comes in a functional reactive programming DSL. The reason to have that is modularity, as we'll see later. And the key thing is a type-driven migration of the state of the program, and it's completely automatic. But you can also extend it manually by user migrations, and we'll see. Well, I'll hint at what that means. So why have I chosen Haskell for this? So you might know that there's something like live coding already exists in Erlang in the 90s, and even in Smalltalk in late 70s and 80s already. But it's a bit different if you do it in Haskell. Well, first of all, it's a general purpose languages like the ones I've just mentioned, quite contrary to a lot of live programming frameworks that already exist. And what you can do is what you can do in Haskell is you can implement all of that without changing anything about the language or about the tooling you need. So you use your normal editor, your normal compiler, everything, just all the normal tools you can use, and you don't need to change them. You can implement live coding as a library completely. And these 2 points are quite different from how you would usually do that. So if you do sound live programming in Haskell, you would, for example, use a super collider, but that is basically a server where you can upload your sound program, and the kind of functions that you can compute there. They are very limited. They're exactly limited to whatever super collider offers you, and you can't do general purpose things in there, basically. Why Haskell is a good target also is because you can compile it to a native code, so you can just run your program on your machine, but you can also compile it to JavaScript in principle and have it in the browser. And what sets it apart from Erlang and from Smalltalk is that you have a very rich type system, and that actually helps you when you do live coding. You might think at first it makes it harder, but it actually helps you, as we will see. So let me give you a little demo on how this looks. So I hope you can still see that. So what I'll just do is I'll start relatively standard daemon called GHCID. There's basically a daemon that automatically reloads your code whenever it changes. And you can see here I've implemented sort of 2D mini golf. Can click somewhere, so you can see how I click, but whenever I click, then the ball starts to move. So the program has some state. In this case, it's the position of the ball and the velocity of the ball. I can change something about the ball here. For example, okay, now I've typed something wrong something that doesn't compile, which is fine. Program keeps running and doesn't restart, doesn't crash or anything. Now I've written something that does actually compile, and you see how the color of the ball has changed to red in that case without anything else changing. So the ball doesn't stop, the program doesn't restart. It's just in the middle of the execution. Whenever it compiles what you've written, then the program reloads in place and continues from. So how does this work? For that, I'm going to introduce what my abstraction for a live program is in that context. It consists of 3 ingredients. The first thing is an internal state. Internal state in this example was the position and the velocity of the ball. Then you have a state transition function. Basically tells you if the last state was a certain position and a certain velocity, then from that we can compute the new position, probably by just adding the velocity to the position with a certain time delta multiplied, and computing a new velocity. In this case, you've seen there were some obstacles, and those are used to compute the new velocity then. And the third part is side effects. In this case, it's things like getting events, like mouse clicks from outside and drawing on the screen. So in a lot of programming languages, that would just be a normal part of any function, but in fact, in Haskell, side effects are treated separately, and they show up with a monad in the type signature. So let's try to capture all that in code. What does the code look like? And this is what you get if you write what I've just said down in code. And this is apart from one line, this is actual library code. This is the actual library code that runs, you've just seen. So live program consists of the following. First, you have this M here, that's the monad, which specifies which kind of side effects can happen. Then you have an S, that is the type of states that can occur. So that in that case, here, it would be a tuple of a position and a velocity. And now a live program, given those 2 parameters, or given those 2 pieces of information, a live program has a state, and it has a step function, and the step function takes an old state and produces a new state under the application of some side effects in M. So you have your state, you have your step function, you have your side effects. Running a live program is quite simple. So the semantics of a live program is basically take the live program, we execute the step on the current state, and we get a new state. now we set the current state to this new state and keep on running the live program, and do that forever and forever and forever. It's not necessarily an eternal loop, because M can also include exceptions, or maybe a monad to stop the program. So having this completely polymorphic in M has a lot of benefits. First of all, you can have, if you want, determinism. You don't need to have any I/O. So that was actually also the reason behind my question to the last talk. Because if you can specify everything in your program completely algebraically, then you can reproduce how your program runs, including everything like concurrency or scheduling or anything like that, or parallelism. You can reproduce that deterministically, and that is really practical for testing, for example. Testing and debugging becomes magnitudes easier that way. And what's also nice is that you can bind to a lot of different backends through that. So often in Haskell, some particular backend comes with its own monad, and then you can just insert that monad there, and then say, okay, well now we have connected to a certain backend. Like, for example, here we have a monad for this graphics stuff that you've seen. So here's an example, not the one that we've seen, but one where I want to explain to you how the migration works, the state migration. So first, let's specify some state. You can think of that a bit like a model view controller architecture, a very simple one, where the model is this state here, and it just consists of a number, the number of visitors, and we want to write a web server now that keeps in memory the number of visitors to that website and increases that every time somebody visits the website. So the server works like that. Basically, it starts with one person. So you have one visitor when it's visited first, and then the step function just does two things. It has a side effect here. It says, let's greet. Let's write a greeting. I mean, usually you would do something like HTML, but here we'll just do it on the console for simplicity. We show the current number of visitors, display a greeting, then we increase the number of visitors. So this server is actually parameterized, and you can insert different greetings. So let's say we have an old server that says, well, greetings number 23, or whichever number it is. Now you could change this program. You can change the greeting, for example. You could say, well, instead of saying greetings, we say hi now. Then the idea is you run the old server a few times, then you exchange the program, and then you have the new server with the old state running and saying hi number 3. So it would be nice if that was the end of the story, but of course that's a joke. It's just starting to get interesting here, because often we will change the program in a really interesting way. You might change the state of the program. The state, sorry, I should say not only the state type. That is the interesting change you can make. Let's say we don't just want to display the number of visitors. We also want to play the last time that somebody has visited the server. So let's modify our program. We modify the state, the initial state only slightly. We give it some random timestamp that we've chosen as an initial timestamp. And we also save this timestamp here as a further side effect. We get the current system time and save that in a variable. Now, how could we go from the old server that only had the number of visitors to this new server here? It doesn't work like that. It doesn't just work out of the box, because the new state has a different type. It just wouldn't type check in any way. So how do we keep the state if the type of the state changes? So this problem is actually a well-known problem. For example, in databases, you have it as well. What you have to do there is whenever you have a program that is newer than the data of the database, you have to migrate the old data. And here we have to do something similar. We have to migrate the state of the program. But it should be automatic. In a database, you write a migration whenever your schema changes, and that's a planned operation. You don't just do that on the fly. You add a migration manually. But here we don't want that. When we do live coding, we don't have time to just write a migration every time we change the state of the program. We want this to be automatic. And actually, in the example, it's kind of clear what it should do. It's a very, very mechanical process that should happen here. Because from the type, we would expect that the number of visitors, there's been no change to that field. It should just stay the same. It should 10 visitors, and then suddenly you add this this time of last access field, then the number of visitors should be preserved clearly. But for this last time field, you don't have any way to guess a new value out of thin air. You have to initialize it from the initial. So those are the two choices, and basically for any atomic field you might have in your data type, clear every time just from the type definition, which so we can sort of mechanically get a good new live state by combining the old live state, number of visitors, and the new initial state. So to express that in a type signature should look something like this. So here we have the new initial state and the old live state. We want to combine those to a new live state, and it should contain as much information from the old state as possible, and only update from this initial state as is necessary. Only that much that is necessary in order to make this here type check. So if you want to guess, you can, and you're a bit knowledgeable in Haskell, you can find a function that has this type signature. So if you want, you can unmute and shout it. Sometimes people know this. It's a well-known function named const, unfortunately. A function that takes this value here and discards that one completely. But that's, of course, the worst thing that you could do. That would mean that you lose all of your data every time you migrate. It's clearly not what we want. We want something better. We want to preserve old fields if they are the same, for example. And you can actually do that in Haskell pretty well using generic programming. And there's a type class called data that allows you to inspect the shape of your data. Basically, you're allowed to inspect the fields of the record. You can look at it as if it were JSON or something like some serialized format. You can inspect the data type constructors and so on. And using that, you can just migrate as much as possible from the old from the old state here. But in a completely type-safe way, so you're guaranteed it will not crash. There's saying the new schema is definitely preserved, or it's definitely valid. It has a few features. For example, what we've just seen, if a record field stays the same, then it's preserved. If things, then they are preserved. There's other things like if you convert to those automatically, and lots of other things that are usually the right thing to do. And you can also extend it with a user, but you don't have to. So that means we have to update our definition of the live program by just one line. And it's this one, we basically have to say, well, every state type has to be inspectable like this, which means that the state type can suddenly not be anything at all anymore. For example, the state can't be a function. It has to be some kind of data type. So it can't really be a closure that expects any further arguments. That's the only restriction. But otherwise, this migration process is completely derived automatically and safely from the state type. And that's a great advantage that Haskell offers you there. Now I'm going to tell you what this might have to do with functional reactive programming. Because what's missing here is modularity. Basically, right now, you'd have to write a big block of state, but we would rather like to build up our whole program out of small building blocks. And if we do functional programming, we probably want to have functions, so we want to have inputs and outputs in our live programs, which makes them to what I call cells. The cell is nearly the same like a live program. The only thing it has an input A and an output B. And the input type and the step function now also takes an input and it produces an output. Now, cells then automatically have lots of nice properties. You might also know them as effectful Mealy machines or state machines, state transition systems, transducers. These are well known since at least the 70s or maybe much earlier. And one thing is you have a trivial cell which just passes data through. You can compose cells. This is how you would write that in Haskell. You can, but you can do more. You can also you can wrap functions into cells, pure functions, also effectful functions in the same monad, and you can also compose two cells in parallel. And the type signatures for that you would see here. And what you can do then finally is you can take cells and use all these properties that they have and combine them to live programs. And one standard pattern that you will see is you have some sort of sensor, some sort of data source that produces something of type A, and it uses I/O, for example, that measures from some device or listens on the internet on some socket or something. You have a signal function then that makes B's from those A's. And then you have something that acts, maybe it sends something back or whatever. And now you can compose all of those. And if you have no input and no output types left, then the definition of a cell just reduces to a live program. So we are back in the live program world where you can do all of the live coding that I've showed before. So you can compose your whole programs modularly. And the key thing is then that all of the state migration functionalities that we have previously, they just work for all of these different kinds of composing cells together. So whenever you build your program and you add a little cell here, you remove a little cell here, then all the other cells in your whole big network are going to just keep on running the way they were before. And that's what makes it really easy to live program like that. Okay, here I have to ask quickly, I'm not sure how much time I've left because I'm not sure when exactly we started.
You have about 15 minutes, including questions.
Okay. Including questions.
Including, yes.
All right.
You can choose how much to leave to questions.
Okay, all right. because I guess there are a few things that are more specific to a Haskell audience, but I don't really want to bore you with all the Haskell details, but rather talk about what you can do with this in general. So that might be more interesting for most of you, I guess. Just a quick side note, what Ivan said before, there's actually a similar construct that is monadic stream functions that was mentioned before, and it's related to this. There's a precise mathematical relation that I'm not going to talk about, but we can chat about that if you're interested. Right, and I'll just leave this part with a little example for a cell. So, for example, if you want to accumulate all incoming data, let's say we have an incoming stream of natural numbers or integers. And we want to accumulate that and return the current sum. Then we can write a cell like this, can set the initial state is 0, so the first result that is being returned is a number 0. And then every time we take this accumulator and we increase it by the number that came in, and we return the current accumulator. So that's some, basically, if you give it the values 1, 1, 1, 1, 1, 1, 1 all the time, then it will output 0, 1, 2, 3, 4, 5, and so on and so on. And of course, you can build more complex cells like that. But often you get away with very small building blocks. You never need to build big cells. You can reuse a lot of cells. So for example, to get a very, very simple FRP, you can say, well, we have a constant step rate, and then say, well, okay, I'll say my integral is just a cheap Euler integral, which means we take an incoming signal, we divide it by the step rate, make the step rate into a function, and then compose that with the sum cell we just had. And then you have a cheap integral. And in fact, it's the integral that I used in the graphics example I gave you. And in fact, I think I'll skip the bit about arrow notation. You've heard before that in the Haskell world, there's a bit, arrows are a bit controversial. Let me just say that arrows are quite niche, but they are good for exactly this purpose here, and probably for no other, but for this, they are a pretty good fit. And you can look at my presentation later for a few examples in order to get familiarized if you're interested. All right. What are a few other features we have? I think I've shown you how to launch this in interactive GHCI. It launches the live program in a separate thread. You can reload it and the program keeps running. There's also a sound adapter that I'm not going to show you because it's going to sound horrible over my laptop speakers in my microphone here. But if you want, you can try that out if you have Linux and Pulse Audio. Oh, there's one great advantage that I've hinted at earlier is quick check. So if you have a cell, you can test the output of that cell and generate arbitrary series of inputs with quick check and test whether certain properties of your cell are satisfied. So you can basically you can property test your cells. It's like stateful property testing. You can also take those tests and you can do them before as well. So that's good if you want to catch bugs before you want to do the migration. And you can do all of that automatically. And one thing that you can also do is you can automatically generate arbitrary state for your live programs or for your cells in order to test. And that it gives you a very thorough way of testing whether your cells will behave correctly. But you can also debug programs, and here debugging is, I'm saying that very loosely. I mean, you've seen a proper talk about debugging already today, but I basically offer a very simple general framework for what a debugger is, and it's basically another live program that can access the state of the inner live program that is being debugged. So basically, you have a live program that takes any state of another live program and can modify that. And I'll just show you how that can look like. So here we have the same example as before again. And while the program is running, I'm just going to switch on little debugger here. It's going to reload, and it gives you some big line, which right now is probably not that interesting because it doesn't break, and we can't really see what is going on here. But it basically contains, basically displays you the state of the program, and if you can display that in a cleverer way than I've done here, then you can look at what your program does live. Yeah, this is what I've just shown you.
Oh, it looks like we've lost Manuel from the stream.
Yeah, either he lost the connection or he just pressed the wrong button or something by mistake.
We'll just give him a short minute to try and reconnect. I'm sure he's frantically trying to find the Zoom link again.
Hi, can you hear me?
Yes, you're back.
I don't know what happened. Zoom's having a really bad day today. Okay, where was I? I think I was about just to show you one little extra perk that actually in this program there's a little web server running in the background.
We don't see your screen.
Oh, sorry. Yeah, makes sense because I need to share it again. Okay. You should be seeing something now.
Yes.
I guess. All right. So just for fun, I made a little server that is running locally here, and I can send it a request. And whenever I send it a request, it gets parsed as a velocity vector, and then the ball starts to move in that direction whatever I specify here. I can move the ball around by sending it HTTP requests. And you can connect all of these different backends or whatever you have, whatever functionalities, you can connect all of them together in a type safe way that it will always work together. And it's pretty easy to use like that. Talked about user migrations. There's a few other things that I didn't show you now, but I'll display some links at the end where you can read up if you want. There are lots of backends that I don't have support for yet. Would be nice to implement those. And there's, of course, all of the pitfalls that you can have in asynchronous programming. Like, for example, here if we have web server and graphics which run at different speeds, then you might want to synchronize them in some way or make them talk together and without data loss and glitches, which has been talked about a lot today. And there is another library that Ivan and me have worked on, and it would be great to integrate it with that because that already solves all of these problems. And the integration is going forward quite well, actually. And another interesting thing would be having even stronger type systems, not just Haskell, but maybe something like Liquid Haskell, where you have a Z3 solver that can ensure even stronger properties of the state of your programs. That'd be interesting, but I don't know how that could be done, to be honest. And that's it. Thanks.
All right. Thank you. All right. So we have just about 5 minutes for questions. you can either raise your hand or unmute yourself or put a question in the chat. I'll start with a question. And my own question is, you mentioned a little bit about using this for audio. I'm curious if you've experimented with live coding performance with your framework at all and how it feels to actually do live coding in real time with this.
I did, in fact, give a performance at ICFP this year. There's, at ICFP, there's a farm, the farm workshop, which is functional arts and reactive music or something. But they usually have an event, and I performed there, and I gave pretty much this example, but also with sound. And it sounded horrible, as I mentioned before, but that's just because my speakers are so bad, and because I don't really know how to do electronic music well. I can program and I can do music, but I don't know much about the mixture, in fact. But it's really easy. You can add an oscillator, and you can add you can maybe show that in the code even. You have an oscillator, and you can specify the frequency, and you can change it, and then instantly the frequency of the sound that you produce changes. So on. So it's nothing about interesting musical structures. I think you need a different, or you need a library on top of that in order to capture interesting music. But in order to just produce sound, it works pretty well, actually. It's a heavy load on the machine because it computes all of the samples and on the machine itself, it computes them in Haskell. But it works. Eats 100% of your CPU, but it works.
Very cool. Very cool. All right, we have a raised hand from Sam.
So when a programmer changes the structure of the state of the program, and he writes a migration to to update the state from the old one to the new structure, and if he somehow introduces a steely bug in that migration function, does that then mean that the program is permanently broken, or can he somehow rectify that?
So at first, your program is basically broken then, yes. So let's say, for example, I don't know, you have this example with a web server with a number of visitors, and then let's say you have a migration function that flips the sign, and then you have a negative number of visitors. Then yeah, that's something that you have to live with, and you have to do another migration or something like that would change that back. So there's no support for something like time travel also. Or there's no support yet built in. It could be added in principle. Could have something like time travel and then say, no, let's go back to the last migration, or let's go back 1 minute, or let's go back 1,000 time steps or something like this. But I don't have that yet.
Okay, thank you.
I have a follow-up question related to that, if I may. It'll be just 1 minute.
Sure, please.
So I forgot what the type signature was, but could you do something like that, time travel, with a specific monad that knows about time travel, that kind of like remembers part of the history up to a time or something like that? Does that even make sense?
I'm not so sure whether you would do it in the monad, because the problem here would be that see, this type S here is existential, so that the state type never leaks to the outside. I didn't really make a point of that. It's important for the implementation actually to work well. And here you have the monad, which is visible on the outside. Also, and in fact, you can't change the monad at runtime. So you can't really make a state monad out of this. what you would rather do, I think, is just a function that takes a cell and makes another cell from it. It takes a cell, basically looks at its state, and let's say the state is an integer, and then it says, okay, we'll make a list of that state type out of it, or a vector or a sequence or something. And then it, instead of just updating it in the step function, it will just append it. So it will change the step function in order to make the step function aware of that. And then you could, in principle, add an extra input to your cell and say whenever that input is activated, then we'll go back to the last element of that sequence or something like this. Because something like that you could do. That wouldn't be too hard, actually.
Thanks.
All right, so we are at the end of this session. I do see one more hand raised, so I'll just first mention that this is the end of this session, and we'll return at 2 o'clock for the next session of this workshop. But I guess if you have further questions, we can continue conversation here in the next 40 minutes, which would sort of be the equivalent of a break.
Yeah, I'm definitely happy.
All right, so yeah, this is the end of the session officially. We'll continue to chat and return for more talks at 2, and in the meantime, we'll just have some informal discussions.
So I still had a question about event sourcing. So instead of transforming your state from one version of the program to another version of the program, you can also accumulate the last n events that have happened. I don't know if you have heard about Redux, which is a JavaScript framework for React, I think. And there they make it possible to make snapshots, and then instead of transforming state from one version of the program to another, they can just replay the last number of events. So my question is, have you thought about integrating something like that in your framework?
Yeah, so that's actually one thing that I'm working on. I don't know this JavaScript library that you talked about well. I've just heard the name once, so I didn't know that it does that. I think it goes a similar way like Ivan's question. So instead of capturing the last n states in the internal state of the cell, you could also say, well, the input has to satisfy this data constraint, and then you could easily capture the input, the last inputs. In fact, so for example, the sum cell here, instead of just accumulating here, you could also just append the A to an accumulator. You could say the accumulator is an empty list at the beginning, and then you could append it there. So in principle, you can do all of that. In order to say how I would ideally implement that and use that, I would actually need to look at the use cases more. So far, I haven't needed that so much in live programming, but yeah, don't know what is a typical use case for that, because I need to know.
The reason why I thought about the question was Sam's question about that once you end up in an erroneous state due to a faulty migration, then you might use a similar technique to make sure that you can always go back to the safest state when the state was correct. And then you can use event sourcing to just replay the events that have happened since then.
Oh yeah, you mean like what's it called? Yeah, basically you want to reproduce that bug that you just saw, and yes, yeah, that's a very good application. So I think just recently somebody asked me for a similar feature like that, and yeah, so I guess I need to get around to implementing that here. But it's definitely possible in this framework because it's very general, and it's definitely possible to add that on top. Yeah.
Okay, thank you.
Okay, if there are no more questions, one thing I'll just ask is for Yvonne to put back the the next session begins at slide.
Yeah, I'll do that. And yeah, the next chair is Manuel. So Manuel, I may have to step out because I've just been called to a meeting. So I tried to move it to 1:30, but if that's not possible, I may have to step out during the next session. So I'm going to make you co-host as well, so that you can do whatever you need. And if I'm not responding, if you try to say something to me during the next session and I'm not responding, then just, I don't know, send a message on the chat or something like that, and I will try to come in. So let me see if I can do this. And now I can. Can you all see that?
Yes.
Okay, perfect. Mark, thank you so much.
Thank you.
Pleasure to see you again. Well, virtually, but pleasure to talk to you again.
Yes, thanks for sharing. Adrian, are you already here?
Yeah, can you hear me?
Yes. Can you quickly test whether you can already share your screen? Because I'm not sure it works because Van is still sharing it.
So let me do that. How's that?
Seems to work. So right now it's still a black screen for me, but this tells me that it's showing your screen.
But I'd still like to see the chat. Okay.
I'll look at the chat in Zoom and the chat on Clouder and let you know if there is a question in there. So you don't need to read it if you don't want to, but of course you can if that's possible.
Yes, I've got it now, I think. Can you see my mouse move?
Yes. I can.
Okay.
All right. I'm very happy to have you back here at Rebels. And I'll chair the third session for today, which has 2 talks again. And the first talk is by Adrian Leinze. You must pronounce your name again because I've certainly not done it as okay. And you have the very interesting promise of doing concurrent programming without processes, which nearly sounds too good to be true. So we're all very excited to hear what you have to tell us. So take it away.
Thanks. Okay, so this is kind of what I'm working on. And yeah, it's just early stages, but here goes. So I really like functional programming. I guess many of you like it as well, but I'm really kind of strict about it, so no I/O for me. But unfortunately, you can't write distributed programs in a purely functional way because like right now, everything is written in this kind of functional core imperative shell kind of way. And even like a distributed language like Erlang is full of these impure imperative constructs like send and receive and spawning processes and monitoring processes, even though kind of the core language is supposed to be functional. So to make a purely functional programming language where there wasn't one before, you have to think about how to model the what of the program, kind of the meaning, and not how it does things mechanically. And of course, we all know functional reactive programming, I think, by Kona Aliot, who also likes to call it denotative continuous time programming, in which programs are modeled as functions of continuous time. So this allows us to, just stuff you would, local programs where you would usually use like callbacks or whatever to make things work. You can now write them purely functionally. And it's got two main data types that it adds to regular functional programming: behaviors and events. And behaviors are semantically functions of continuous time, whereas events are partial functions of time. So like a really simple program would be like time itself, which is a behavior that's time valued. So if we pretend time is a real value, then that's what it's going to be. You can easily construct new programs, for example, this kind of bouncy behavior that's going to follow a sine wave just by mapping the sinus function over time. And you can compose two behaviors. For example, the previous bouncy function, we can make it like go up as well by adding time to it. By the way, you can ask questions if something's not clear and stop me at any time. Okay, so let's look at distributed programs. What's the problem with FRP? So we've got time here, and so there's only one notion of time for all places. So even if you kind of like try to write distributed programs in FRP, you would really fail because it goes against physics, and there's no such thing as like a global time. And you can kind of sense it from the word distributed program, because distributed means distributed in space. So we just have to kind of add space to the semantics. And this gives us denotative continuous spacetime programming, where behaviors are functions of continuous spacetime and events are partial functions of spacetime. And for this talk, I'm just going to say spacetime is a pair of space and time. Of course, distributed programs are not just about like multiple programs running at different locations. A kind of essential thing about them is that messages are sent in between and that information travels between points in space and time. So we will model this with a binary relational spacetime, which I call perception, and I'll use squiggly arrows for them. And so, for example, if you look at like a classic distributed log diagram thing between two locations, you'll see that at time 0 at location A, a message was sent which arrived at location B at time 1, and then it sends back a message which arrives at location A at time 3. So we can just say like location point in spacetime B1 perceived point in spacetime A0, whoops, and point in spacetime A3 perceived point in spacetime B1. So let's look at a simple program called ping. So we all know ping. It goes something like this. You write ping server, press enter, and it starts by saying pinging. And then when it gets a reply, so when it says pinging, it will send a message to the server and the server will send a message back. And when you get this reply, it will print at what time that happened and continue pinging. So this will lead to like a perception diagram kind of like this. And so we will write this program in DCSP, but I'll first show you some primitives. So a really simple one is space, that just always returns the space component of a behavior. I'm also using now, which is an event with a single occurrence at the moment the behavior is sampled. And then there's perception at, which from a certain event with occurrences in space and time, tell us, so give us a new event, which are the perceptions of these first event occurrences at a particular location. So if you look at my really bad drawing, you have all these points in space and time, which are perceived at other points in space and time, so here and here. And we just want those that are perceived at location B, for example. Okay, so one essential component of ping is this kind of round trip behavior. So we send a message to the server and we wait for the reply back. So we can encode this behavior perfectly in DCSP. So we'll get this now event. So that's here, the here and now. Because this round trip behavior, this program models like an infinite amount of round trip programs, which you have to like sample it as at a specific point in space and time. And that's the start of the program. So this here and now moment that we sampled, we want to know when was it perceived at 2. So in Ping's case, that would be the server. And that's another event with a single occurrence. And then for the place of here and now, like the point in space of here and now, L, here, L, we want to know when that moment of perception at the server is perceived back here. So with this round trip program, we can easily write ping, like one round of ping, just by saying, okay, I want to know the round trip to the server. And from this reply, I want to know the difference between the point in space and time when the program started, like this T0 is the local time. And we're gonna generate a message reply after the difference between the time at perception. So this reply event, which has one occurrence here. And that's going to be the result of one round of ping. So then we want to run ping forever, because when we write ping server, it just keeps pinging forever. And that's just regular FRP programming and regular functional programming the way we know it. So we'll make a recursive program, because you'll see that ping appears in the body of the program itself. So ping appears in itself. And it starts out by saying pinging, and it will kind of run between, it will run one round of ping after, and then append the result of ping 1, and then continue with the future ping. So that those are future is the recursion to ping. And so this will be like an infinitely long-running program, which is kind of recursive over space and time, and not just recursive over time only, as classic FRP is. So how would you implement such a language? Well, the really easy way is to just send everything that happens to everywhere, and then you would even have to like simulate all places at all places. So if you have a particular behavior, you have to kind of know what its value is everywhere. And it will all be very slow. But luckily, I also have a feasible strategy. And that's to take any DCSP program of type A, and we'll turn it into an FRP program, which takes an input event of environments, and I'll say what that is later, and an output event of environments. And these environments are a mapping from identifiers, which identify each use of perceptions to some serialized value. But to do this, we need to force a structure on our program. And so all like feasible FRP libraries, which are used to make like real programs, for example, Reactive Banana and Reflex and FRP Now, use this strategy. And I think also kind of errorized FRP kind of implicitly does this. So for example, perception, where it just used to return an event, it will now return this event in the context of this now data type, and stepper, like this classic FRP function stepper, will also return inside this now data type, and so on. But semantically, now is just the same as behavior, except with this kind of notion of from now on, or in the DCSP case, a notion of when something becomes known, because information has to travel. So there's this thing called first order FRP, which is quite common. Like even in this Rebel session, we've seen lots of first order kind of reactive programs. And those make sure that you can't do anything useful with events of now or behaviors of now, or events of events or behaviors of events. And this forces a kind of static structure on the program. So then our problem is really easy, because we can just statically number all uses of perception in kind of the program text. For example, in round trip, we can call this one the first and this one the second. And this is the approach taken by Gaviel. So DCSP is not really the first distributed FRP, but it's the first kind of like generalized distributed FRP, which is just as flexible as FRP. And so Gaviel uses this first order technique. But of course, first order is very limited, as Steve Krause told us 2 years ago. So if you want to learn about that, why first order kind of limits composition and stuff like that, I highly recommend you look at this. So let's see what a program run might look like for first order FRP. So again, you have this kind of this starting moment at a certain place. Let's call this A. And it's going to send, okay, for the input argument to the first perception, this now event, that's just like a unit valued now event. So it's going to say, I have an occurrence for that one, and it's going to send that to some other location. And that one is going to look at this perception coming in, this event occurrence coming in at number 1, and it's going to say, okay, then I have an event occurrence at event there, and now I have to send that to everywhere under number 2. And so it just sends that to all other locations, and then we know that there's been a round trip. For higher order DCSP, this problem is kind of much more complicated because now you have this function like run now, which will kind of run operationally then these DCSP programs, which might happen at any point in space and time. And so you can no longer kind of number all uses of perception because there can be like an infinite number through space and time. But we can encode this in the identifiers. So at this kind of the start of the program, we can still use just the number, but then we will add, we will make identifiers longer and longer so that they kind of contain the whole causal trace of what happened, the causal trace of what led to a specific perception to exist. So that's what's going on here. So we'll say to make a new identifier, attach the point in space and time that this program is run, attach the number of perceptions, and this can be done like recursively, so you can get like an infinite number, infinitely long identifier. So let's look at this round trips program, which is kind of like ping before. So it contains this kind of first order only program round trip here. And then it's gonna run the whole round trips program whenever we get this round trip event. So we also have to give run now a number. So there's 3 numbers now, 1, 2, 3. But this run now thing will kind of generate longer and longer identifiers. So what does that look like? So again here at kind of the start of the program at A0, it's going to send, okay, for perception numbered 1, I have an event occurrence, and then that's going to be perceived somewhere. And that other location is going to send the message back on number 2. And once A receives this message at point A1, it's going to say, it's going to send like a more complicated environment than before back to B. And this consists of, so the relevant number for run now, that's 3. And then it's going to say at A1, this program, so this is like a serialized representation of round trips, was run. And so please run it too so that you know what's going on. And this run also has an occurrence, that's this here again, which has an occurrence at the same time as, because it's here again twice. So this is sent to B, which is like, okay, which receives this and now knows that it has to listen on the identifier 3 and then A1, 2 for this second perception. And it's gonna send back on number 3 the same as before. And then A is again gonna say, okay, now we have to start a new program with the identifiers from before, but 1 level deeper. So you'll see that these identifiers are becoming longer and longer, but that's not really a problem because you can just hash this part and have kind of like a fixed length identifier. So I hope that kind of makes sense. It's confusing to think about, but hopefully in the future I'll be able to explain it better. So right now I've got this implemented in Reflex FRP. I haven't published it yet, but you can ask me for the code and I'm happy to send it to you. And I can implement, for example, ping. It's kind of messy and ugly, but I've got this little DSL for describing communication patterns. And I've got it implemented as an executable semantics. And by this implementation strategy I showed before, and I have this function which compares the two and tells you whether the output of both matches. And I can also write Paxos, but I'm really ashamed of it because it's very messy. But that works too. So you can write complicated programs, but because really what this is lacking is a kind of like domain-specific language to describe distributed algorithms. So once you would have that, Paxos would just be a few lines, and I'm working on that as well. So what's left to do is to add a distributed garbage collection mechanism to this implementation strategy, because right now the implementation will just like keep listening at specific identifiers and keep sending around event occurrences, even if they can no longer influence like the output of the program. And then the denotation of continuous, of denotative continuous spacetime programming suggests that we should be able to do useful things with a really continuous spacetime, because right now I used like a very limited notion of space and kind of limited notion of perception of like information travel. But maybe like inspired by physics, you could think of much more complicated programs which deal with distribution in a more abstract manner. And as I said, what's really important for the kind of DCSP I described here is to have these DSLs for algorithms, which will make everything very succinct yet composable. Okay, so that's my talk. If you have questions, fire away.
Thanks a lot.
Thank you.
So we have comfortable time for questions. So if you want to ask a question, feel free to unmute. Or if you don't want to ask it yourself, you can also post it in the chat and I can read it. If no one wants to ask a question right now, then I'll go first, maybe. You've written this following the philosophy of classic FRP, and as you certainly know, one of the dreaded first class of bugs haunting classic FRP were time leaks and space leaks. Basically, a time leak being the problem that if you have something that depends on an arbitrarily long history of some other signal, then there is then the program will take longer and longer to execute. And do you have something similar here, or could you in principle have something similar like this here? So before there was something where you briefly hinted at these identifiers getting longer and longer, but you had a workaround somehow. Do you in principle encounter that problem? And yes, so how do you solve it?
Yeah, so as I said, so I implement this and everyone can implement this on top of like a non-leaky FRP implementation. But the distributed part is leaky because, yeah, I wasn't very clear about these messages. So I just had two locations here, A and B. But these messages, they have to be sent to all other locations, even if you only have like a perceptions at primitive. Like you can't just send it to the target of the at expression. So that's a very leaky thing because it will generate a lot of network traffic. And yeah, what's left is kind of like hooking into the garbage collection mechanism of an existing FRP implementation, because you kind of have to stop sending the event occurrences when no one is listening. And right now it just keeps sending all event occurrences of an event that's ever been the argument of perception. And that's just only gonna grow. So it's also kind of like a space-time leak aspect of it. So yeah, the leaky bit is mostly just lots of network traffic that doesn't have to happen.
We have another question so far.
Yeah, I've got a question.
Please go ahead.
So yeah, it's a very interesting talk. So one of the things that you need to do in order to implement an FRP system is you need kind of like universal consensus on the fact that nothing else has happened up to time t. So if I've got an event that I think I might be firing at time t, I'm going to wait to make sure that there's no events before it, so my state is up to date before firing my event, and so the way I've implemented that in the past is by allowing every node in the data flow graph to ask its neighbors, right? Are you going to tell me anything up till time t? And once they all say no, right, now I can proceed. And I'm wondering, that kind of consensus is fairly cheap if you're on a single node, but it seems quite expensive for a distributed system, because essentially it's global consensus. So is that something that you hit about having to send lots of negative messages around?
So this depends on the precise details of the perception relation. So you don't have to send anything around that you don't want to, but less things will happen if, like, it depends on the precise implementation. But for example, if you use causal causal delivery, then you do have to kind of wait around for, like, to get the whole history if you receive something like from the future where you haven't received the past of that location, stuff like that. But this really is agnostic about kind of the delivery guarantees. So the only thing it wants is that the environment gets generated at a particular point in space and time at a certain location needs to be transferred and as a whole. You can't like split it up or something like that. But that's really like the units of transmission. Apart from that, you don't have to wait around more than you want.
Okay, so what are you assuming about that, or that the perception relation? Are you assuming that it's an order? I mean, is it a partial order? It's certainly not a total order.
So the identifiers I'm using here, they have to be, it assumes that it's like ordered delivery. But you could easily extend this with, I think, kind of like the moment a program became known, like put that in the identifier, and then you're free to have like completely random, like the least guarantees of networking that you can do, and it will still work.
I think what I'm wondering about is whether there's some transitivity properties you've got that are you know, if Alice and Bob have got their shared state, and Bob and Charlie are also communicating, you know, one of the things that Bob might be communicating to Charlie is information about Alice. So how does are there any guarantees that what Charlie is finding out from Bob about Alice agrees with what Charlie's finding out directly from Alice?
No, so unless you use causal delivery, stuff that mentions something that you haven't heard of before, like what that's going to be is like a part of an identifier where you don't know about the genesis of that identifier. So that's just going to be ignored. So it will make for a lot less obvious behavior of the program, but it's still perfectly possible to describe it denotatively.
Mm-hmm. Thanks.
Yeah, I hope I answered your question. Feel free to email me if it's not clear.
Are there any other questions? If not, I might venture further one. That's okay. I think we still have enough time. Basically, what I didn't really understand is how you execute this. Can you execute the same program on different nodes? I don't just mean different GHC or whatever your runtime is, threads, but actually different nodes. And how do you sort of tell your program? You have to tell your individual node like which one it is, so on what to listen to. And or is that basically the problem you hinted at before, that then you have to tell it to stop listening to a lot of stuff that happens here? Is that the issue you had before?
So here, I'm assuming that everyone kind of runs the same program, and it knows what to do from the start. Like, because everyone knows about these first 1, 2, 3 numbers, identifiers. But you don't have to have it like that. You could also have it be more dynamic. But then for anything to happen, then someone would have to start like, okay, this is the program we're going to run, and have to send it to all nodes. And then they can be like, okay, I'm continuing on your program and we can work together after that. But it's kind of, you can choose this. So either you start with like a known program, or you can do the scheme where someone initiates a program and others will only know to run it once they know about you initiating it.
And then how do the nodes, well, I think that's going too far. So, but my question is basically, how do the single nodes know who they are? So they also need to say, okay, I am A in this part, or I am B in this part.
So every like locally running FRP implementation needs to have this kind of space behavior that's filled in for them. Like you have to say you are node A, you are node B. I don't have anything yet to like invent places.
You mean you would have to hard code for each one of them which node number they are?
Yes. But you can still like run them. You can make new ones, but it's kind of like outside of the system. It will still work, but it's not modeled inside of the language.
Like dynamically being able to add or remove nodes to a swarm, for example, or a collection.
Yeah, you can do it.
I don't think that's generally an easy problem. Like once you start adding those things. It
Yeah,
becomes much
so
more complex.
there's the distributed program of group membership management and all those things, but this is kind of agnostic about it. So inside the language, you can't invent new places, but you can like sneakily say, oh, by the way, this place always existed. And yeah, and nobody will be the wiser.
Okay, well, thanks a lot for horizon broadening talk.
Thank you.
I have some 2 minutes where we can set up the next presentation already, if you want.
So if I may, I have an update. So it appears that the last talk today is not going to happen. The one at, well, 4 o'clock for me, and that would be, I guess, 10 o'clock in Central Europe. So 4 o'clock in New York time and 10 o'clock in Central Europe. It seems like it's not going to take place. So perhaps one thing that we can do is after this talk, we can kind of wrap up. I will take 5 minutes, but if you want to take the break off and then come back, I can. I won't take long, but yeah. You don't need to change anything about the talk. It's same length, same length.
Okay.
Ivan, I'm not quite sure what the conclusion was now.
Well, I'm just putting it out there in case someone says, "Oh, I really wanted to take the time off," or "I prefer." Like, I'm open to opinions. If somebody has strong opinions about this, maybe there's something else happening at Splash, and they say, "No, I really want to attend this thing because I'm not aware of everything that's going on at Splash." So I wanted to mention it now in case someone wants to bring up that they strongly prefer to have the break and then come back, even if it is for 10 minutes. But yeah, we can talk about this right after this talk.
Okay, so if no one, or maybe if no one is going to post anything in the chat, then we could just have the closing remarks directly. Maybe that may be acceptable.
Yeah, that would be acceptable for me. Yeah.
Yeah, I agree with Wolfgang that it would be nice to directly round it off. Guido agrees as well. But isn't it your talk, Guido, that is being cut?
Well, yes, but that doesn't mean that I have the presentation ready myself.
Yeah.
But that makes it far more interesting, doesn't it? Because then you have to guess it along the way.
Yes, a little PowerPoint karaoke would be a great way to finish the workshop.
It's like an improv. We just throw words from your paper and then you have to explain what may be going on. No, it's understandable. Yeah.
Okay, well, then we'll have, in fact, the last talk for this workshop, which is about reactive sorting networks. And Bjarno is going to tell us all about it. So please take it away.
Okay, so thank you. So hello, everyone. My name is Bjarno. I'm a PhD student at the Software Languages Lab at the Vrije Universiteit Brussel in Belgium. And today I will tell you all about reactive sorting networks. Now imagine for a moment that you are working as a software developer for a transportation company. As we all know, trucks consume fuel, and lots of it. And you're asked to implement a system to monitor the fuel consumption of every truck in the company. You're currently working on a dashboard application that tracks the fuel consumption of each truck. One component of the application needs to show a ranking of trucks according to their recent fuel consumption. As sensor data continuously arrives into the system, the use of the reactive programming paradigm should be obvious, at least for us Rebels people. Now, one way how you can implement this ranking is to make use of a sorting network. Sorting networks have a fixed number of horizontal lines called wires, and the circle and arrow denotes a compare and exchange operation, which compares the two values on a wire at that point in the network and exchanges them if they are not in the right order. The largest value is propagated towards the direction of the arrow. So the unsorted data enters the network on the left and exits the network on the right. Similar to dependency graphs found in reactive programming languages, sorting networks have a directed acyclic structure with sources and sinks, and a number of computations between the two. This similarity was one of the reasons why we decided to make use of the reactive programming language to describe the structure of sorting networks, and to propose the idea of reactive sorting networks in general, which are sorting networks that sort data incrementally, the same way how a dependency graph is updated in a reactive programming language. We could implement this sorting network, for example, in RE-Scala, a library for reactive programming available to Scala programmers. The function bubble5, as this is a bubble sorting network of size 5, has only one parameter, an array of signals carrying integer values. Each application of the CAE function creates two new signals and stores them in place in the array, such that at the end of the execution of the function, the array contains the signals that carry the input values in sorted order. This is what we call an extensional definition of a sorting network, as it is only a single instance of all the bubble sorting networks that can exist for various sizes. We could hardcode every size, but that would of course be quite tedious. So instead of hardcoding these compare and exchange networks manually, we can use two nested for loops, as shown here. This is what we call an intentional definition, as this function is a program that describes the overall structure of the network. But by building the sorting network in the Scala programming language itself, we are actually using Scala as some sort of a makefile language for constructing dependency graphs. This means that the behavior of the constructed RE-Scala program therefore depends entirely on the execution of the Scala program, which can make it more difficult to reason about the behavior of the reactive program. Now, for bubble sorting networks, this problem is still quite manageable, but if a more complex sorting network would be used, the problems would become more apparent. The existence of a makefile language can give rise to both behavioral and structural problems. If you're interested in learning about these behavioral problems, we have published a separate paper that describes these issues in more detail. It's titled Tackling the Awkward Squad for Reactive Programming, the Actor-Reactor Model. There is a talk later today, or maybe tomorrow, that of course depends on your time zone, about this paper at EGOO. But in the work that I will present here now, we have focused primarily on the structural problems that can occur. The use of a makefile language results in a program where two language semantics can be interleaved, and even syntax can be interleaved in the code as well. In addition, the use of two languages can also result in code whose structure actually doesn't even match the structure of the sorting network. Now, while in this presentation we will primarily focus on sorting networks, our end goal here is to support various types of inductive definitions of networks in a language where these issues are not present. But more about these other types of networks at the end of the presentation. So instead of trying to unify both reactive and non-reactive programming models, we have chosen to completely eliminate the non-reactive part of the language. High, which is our language, is what we call paradigmatically pure. It's reactive all the way down. everything is implemented as a reactor without making use of lifting. Syntactically, high code looks a lot like scheme code, but it has completely reactive semantics. So the code on the right here is an example implementation of some code that can, for example, be used for our aforementioned fuel calculations for the truck company. So the central notion of a high program is that of a reactor. A reactor is an abstraction for reusable components in dependency graphs. In this presentation, we will visualize reactors as rectangles with their sources on the left and their sinks on the right. And inside each rectangle is a hidden dependency graph that describes the behavior of the reactor in question. Reactors can have any number of source nodes and any number of sink nodes. For example, the fuel calculation reactor, as shown here, has 2 sources and 2 sinks. Reactors can also be nested. For example, the fuel indicator reactor, its definition is shown here, makes use of the fuel calculation reactor. Instances of reactors will create the actual time-varying signals. We will call these instances deployments, in the same way that in object-oriented programming languages, instances of classes are often named objects. High is, of course, the language that we will now use in the rest of this presentation to implement our sorting networks. Now, an important insight that we distilled from other reactive programming languages is that they are often executed in 2 phases. One phase that we call a deployment phase, which is the phase where the dependency graph of the reactive program is constructed, and the second phase that we call the propagation phase, where values are being propagated through this dependency graph, while also updating, of course, the state of the reactive program. Now, usually both of these phases are interleaved, but in high, they are separate in execution. So in order to generate sorting networks of varying sizes, we therefore want to make this deployment phase to be as rich in functionality as possible, such that we can use it to generate reactive programs themselves, such as those for sorting networks. Now, before I show an implementation of a sorting network in high, let's first investigate its structure in terms of reactors. A bubble sorting network consists of 2 kinds of repetitive shapes. One shape is that of a vertical stack of interconnected comparators, and the other shape is how these vertical stacks are connected to each other to construct the full bubble sorting network. So let's start with the first shape. When n is equal to 2, n means is here the number of wires, it's quite easy, of course, to stack comparators, as there is only a single compare and exchange operation, which is in this case equal to a reactor that we will call CAE. Now, when n is 3, we need 2 of those reactors, and we need to connect the topmost sink of the bottom one to one of the sources of the top one. So this reactor, as shown here, is a stack of comparators for n is equal to 3, as it has 3 sources and 3 sinks. Thus, in general, when we want to construct a stack of comparators for any number of wires n, we have to extend the comparator stack of n-1 with a new comparator and connect the topmost sink of this new comparator to one of the inputs of the smaller comparator stack. As such, we have created a new reactor with n sources and n sinks, such that the largest value is propagated to the topmost wire. So next shape, how do we combine these comparator stacks to actually construct the complete bubble sorting network? Once again, when n is equal to 2, there is only a single comparator and thus a single occurrence of the CAE reactor. When n is equal to 3, we have to put a single comparator stack of size 3 in front of that single CAE reactor. This is a reactor implementation of a bubble sorting network for 3 values. So in general, to build the bubble sorting network for any size n, we extend the bubble sorting network for n-1 by putting a stack of comparators of size n in front of it. From this intuition, we have distilled the following 3 requirements for our language, which will need to be fulfilled to support these sorting networks. First, our language should of course allow for the implementation of the CAE reactor. Secondly, we need to be able to programmatically glue together reactors such that we can create larger reactors out of smaller ones via code itself. And thirdly, we need to support this gluing together of reactors in such a way that we can generate reactors of varying sizes with repeating patterns. So let's start with the implementation of CAE. CAE is implemented in terms of two reactors named min and max, which are defined as follows. The min reactor has two parameters named A and B, and it will create a conditional signal whose value is equal to the smallest value as carried by the signals A and B. Now, of course, the implementation of the max reactor is quite similar. The CAE reactor itself is thus implemented as follows. It composes the min and max reactors such that the deployments of the CAE reactor will deploy the min reactor and the max reactor on A and B. CAE's sync signals are the sync signals of the min and max deployments, in that order. We use the out syntax, or some people call it a special form, for reactors that have more than one output. So that's CAE implemented. Next, we need to glue together some reactors. Let's think back about our transportation company. Imagine that the fuel calculation always uses metric units. If we want to use imperial units, we need to be able to convert the values that it produces as output for one unit system to another. We can implement a reactor called metric to imperial, which converts one value from one system to the other. But how do we put that reactor at the back of the fuel calculation? We could do that manually, like how CAE was implemented, but there is in fact another way. HI has a number of primitive built-in operations which can create new reactors programmatically. For example, the parallel operation places two reactors in, well, parallel. This makes it possible to create a new reactor that contains two copies of the metric to imperial reactor. To put this new reactor after the fuel calculation reactor, we can use ROR. ROR stands for reactor after reactor. Now, its name is inspired by the mathematical notation for function composition, using a small circle, thus we use an O instead of an A. Using ROR, we have constructed a new fuel calculating reactor whose outputs are now using imperial units instead of metric units. We can actually use the same technique to also pre-implement CAE. Remember that previously we implemented CAE by connecting its sources to both the min and max reactor. Exactly that behavior is also captured by the parallel star operator. Both reactor implementations thus behave the same when deployed. In total, HI has 8 of these operators. We will call them weaving operators, as they take as input one or more reactors whose sources and sinks are woven in a particular way. In the paper, we explain each of these operators with a diagram that describes how these sources and sinks are connected. We call these diagrams Jacquard diagrams, as they are named after Joseph-Marie Jacquard, the inventor of the mechanized loom. Now, ROR, parallel, and parallel star already existed before in some work that I presented here a couple of years ago at Rebels, but these three were not powerful enough to express our sorting networks. For sorting networks, we needed to be able to rewire certain source and sink signals, for which we have added rewire in and rewire out. We also needed to be able to connect the sink signals of one reactor to one of its own source signals, for which we have provided Snake. And we needed to be able to extend a reactor's dependency graph with another reactor's dependency graph, but only on a specific set of source signals or sink signals, for which we have provided pre-weave and post-weave. Now, small remark, HI is using one-based indexing for selecting the sources and sinks of reactor, so it's not using zero-based indexing, as was used in the RE Scala program in the beginning. So we have these weaving operators now, but how can we use them to create reactors that have varying sizes and repetitive patterns? What if we repeat our example from just a moment ago, so what if the numbers of sinks of our fuel calculation could vary. How can we apply our metric to imperial reactor then to all of these things? What we need is a way to place multiple copies of this metric to imperial reactor in parallel. But such a weaving operator is not actually built into the language. But we can make one ourselves using recursion, which should come as no surprise to us computer scientists. By using recursion, we can use parallel as many times as we want to create these kinds of reactors. Parallel n, Rn, is equal to R if n is equal to 1. And if not, the parallel n reactor is deployed recursively to create n-1 copies of R in parallel, and then the parallel weaving operator is used to add this last copy of R to this reactor. What we have actually just done is that we have created our own weaving operator. This is possible as the built-in weaving operators of HI are just available to HI programs as ordinary primitive reactors. They are not part of a separate weaving language. Now, for sorting networks, we will use a number of additional user-defined weaving operators. Their implementation is not really important for this presentation, but just like with the primitive weaving operators, we can draw the Jacquard diagram of these operators. The snake-on weaving operator we will use in our implementation of the bubble sorting network, as it allows one to connect a specific sync signal to a specific source signal, which is not directly possible with the built-in snake weaving operator. So that's everything we need to implement sorting networks in HI. Let's finally look at an implementation of a bubble sorting network. Let's start again with the first shape, the stacking of comparators vertically, which we will do in a reactor called bubble 1. Once again, when n is equal to 2, there is only a single comparator, thus we immediately return or emit the CAE reactor. In every other case, we use a recursive deployment of the bubble 1 reactor to extend the smaller network. We use parallel to place a new copy of CAE in parallel with the smaller comparator stack, which we will call P in the code, and then use snake-on to connect the sync of the new compare and exchange operation to the smaller comparator stack. So that's the first shape done. Next, we will need to connect these comparator stacks, such that we can create the entire bubble sorting network. This we will do in a reactor called bubble. Again, when n is equal to 2, the stack is still equal to the CAE reactor. So in this case, we can just return or emit that single CAE reactor. For larger sizes, we recursively create the smaller bubble sorting network and use a parallel with the identity reactor to create a new reactor, which has as many sources and sinks as the bubble sorting network, as the comparator stack, sorry. We then combine these reactors with ROR to create the complete network. So this is a complete implementation of a bubble sorting network in HI. Once again, this is an implementation that does not rely on a separate makefile language and only relies on the semantics of the reactive programming language itself to intentionally generate bubble sorting networks. Now, some small remarks about the use of recursion in HI. As we mentioned earlier, HI programs are executed in two separate phases, a deployment phase and a propagation phase. That means that the complete dependency graph has to be constructed before the program actually starts reacting. No changes to the dependency graph can occur at propagation time. This means that the number of nodes that can be activated in the dependency graph during a single propagation turn is limited. And thus we can guarantee that the execution time of a propagation term has a constant worst time complexity, regardless of the changes to the source signals. We therefore call HI programs strongly reactive. Now, more information about the execution time of a single propagation term in different program languages can also be found in the paper that I mentioned in the beginning of the presentation, and I will therefore not delve into its details here. To be able to construct the complete dependency graph at deployment time, the depth of the recursion should be restricted. Either an upper bound for the values carried by the signal n has to be known at deployment time, or its value has to be constant. In high, we have chosen the latter. Now, we conjecture that in many cases, that this does not actually hinder any implementation of any reactive program, at least for reactive programs where a growing dependency graph is not an essential property of the program itself. And finally, a remark about higher order reactive programs. As reactors are first-class values, they can be carried by signals. An example of a program that uses a higher order signal is shown here. In this simple program, a signal R is created, which either carries the full reactor or the bar reactor. Thus, this deployment expression needs to alternate between the different propagation turns between these two reactors. Now, we analyze the program at deployment time to know the reactors that these deployment expressions need to toggle between during the different propagation phases, turns. By determining what we call the toggle set of each of these deployment expressions, we can ensure that the complete dependency graph can still be constructed at deployment time. Now, we're currently working on to make sure that this analysis does not actually diverge, which can occur in recursively defined higher order reactive programs. And towards this end, we're currently working on integrating size change termination, but this is ongoing work. Now, for all the programs presented in this presentation, our current implementation actually succeeds. So that's good, I think. We can use reactor signals in our implementation of the bubble sorting network. Instead of always using the same compare and exchange operation, we can add the compare and exchange operation as a parameter to the bubble 1 and bubble reactors, as implemented earlier. In a way, these reactors have now become weaving operators themselves. If we supply the bubble reactor with a higher order signal that continuously toggles between a compare and exchange that sorts from small to large and one that sorts from large to small, we can easily reuse the same sorting network with different sorting behavior, without needing to reconstruct the entire network each time the condition signal changes. Now, in total, we have made 5 intentional implementations of sorting networks in high. So before I end this presentation, I will briefly discuss the implementation of another one, mainly the pairwise sorting network. A pairwise sorting network consists of 3 steps. First, all pairs of wires are internally sorted. Then, all even wires and all odd wires are sorted independently of each other. And then the final outputs of the sorting network are constructed by merging the outputs of these 2 subnetworks. The implementation of a pairwise sorting network in high is thus as follows. We have a reactor called pairwise that creates the sorting network. And then we have 2 reactors for respectively the second and third step of the sorting network. The first step is easily implemented by placing n divided by 2 copies of the comparator reactor in parallel using parallel n. For the second step, where the odd and even wires need to be sorted independently of each other, we first create 2 sorting networks for each half of the inputs, which are constructed using a recursive deployment of pairwise. We then rewire its sources such that the odd wires are connected to the bottom network and the even wires are connected to the top network. For this end, we use an internally defined reactor called loop-in. But of course, we need to do the same thing, the reverse for the outputs. And for this end, we use loop-out, which uses move-out, which is one of the weaving operators that we implemented ourselves in high. The third and final step is thus implemented as follows. We start from a reactor named start, which is constructed by placing n copies of the identity reactor in parallel, and then incrementally add comparators to this reactor according to the algorithm described in the original paper. In the implementation shown here, we use 2 loops, an inner loop, which constructs all the comparators inside each of these red boxes, and an outer loop which loops over these red boxes. So this is a complete intentional implementation of the pairwise sorting network in High, once again, without making use of a separate makefile language. Now, I don't have time to go over all these 5 sorting networks in this presentation, so if you're interested in those, please do read the paper and the accompanying supplementary material. In conclusion, I've presented the following. First, we proposed reactive sorting networks. Reactive sorting networks are sorting networks that sort data incrementally the same way as a dependency graph is incrementally updated in a reactive programming language. From the structure of the bubble sorting network, we have distilled a number of requirements that our language needed for the intentional definitions of reactive sorting networks. One of these requirements is that the language needs to support repetitive patterns. In our language, we support repetitive patterns by allowing recursion during the deployment phase. By doing so, we ensure that High programs are strongly reactive. In other words, the worst time complexity of a single propagation turn is constant, as the dependency graph cannot be modified while the program is reacting. We then used our language to intentionally describe reactive sorting networks. Now, one final word about future work. We wouldn't actually say that our current language is complete. There are a lot of other fields whose concepts could also closely map onto the structure of a dependency graph, and which could also be implemented intentionally. For example, neural networks and maybe even parts of network infrastructures. We expect that we either have to provide new weaving operators, or that some of the restrictions or functionality of recursion should need to be modified, or maybe even both. But finding that out is, of course, part of our future work. So that's everything that I could say right now about reactive sorting networks. So if you have any questions, I think now is the time for those.
Thank you very much for a very clear and enlightening talk. So are there any questions?
Yeah, I do have one question. So perhaps you said it and I missed it, and sorry if that's the case. What would be the main use case of something like this? Like, would you expect that this would be the way that you implemented, say, in software, or would this be something that you would use if you implemented mainly, say, in an FPGA or directly in hardware?
Well, I wouldn't say that it's a really good idea to implement like a language or a variant of High on hardware. But I think the language itself shows that even though you don't have an active part of the language, you can still use the reactive language itself to make different types of dependency graphs. For example, sorting networks that we've shown here.
So I guess what I mean is, if I understand things correctly, once you have, like you described the sorting network, and you have a language for this, but once you have the dependency graph, that's not really going to change. That in size is static. Is that correct?
That's correct. So right now,
would that mean that if you wanted to map that to hardware, then that would mean you have a limited number of components that you need? Is that the reader?
Yes. So if you build the complete dependency graph, you can actually like do a topological sort of all the nodes in that DAG, and then just implement each node in hardware directly or in C code or whatever. That's something that you can do.
Historically, these things were invented for sorting on processor networks, such as transputers.
So I guess it would also mean, and I don't know if it's a pity that Jean-Louis, he's not here. I wonder if in domains like where Jean-Louis Colasso works, where you need limited, like you have, well, you operate under hard real time. You have no memory constraints and time constraints. If there, you would need to resort to something like this, because a general purpose sorting algorithm, if you try to implement it in a different way, you don't know for sure what it's going to take. I mean, I guess you can always use asymptotic complexity to tell what the memory and time complexity is going to be. So maybe that doesn't make too much sense, but
yeah.
Okay. Sorry for the noise. Thank you.
Further
questions?
I have another question, if that's okay. I was thanks. Okay, so first, well, thanks for the very nice talk. I was wondering, what's the reference for the performance of this thing? So what is the right thing to compare to? Well, during your talk, I thought about I think it's called self-adjusting computation, Umutakar's framework for incremental computation. I'm not sure if this is related, if it could be a comparison, but that's kind of general. It works for any algorithm, so maybe it's not really the right thing. So where could you say, well, this is the performance that makes me happy?
Well, to be honest, I haven't actually benchmarked any code so far, which is definitely something that I should do in the near future. But something fun that I found out is that while I was working on these sorting networks, that so the language hi actually runs in your browser, and you can interact in it just by typing in some code, and then it gets executed all in your browser. And sometimes the DOM was slower to update than to actually sort some values in the sorting network. So that's quite promising, but I don't have any like numbers I can show you, like, okay, this is something that we currently have, this is something that we want. So I don't do that yet, but it's definitely something that's on my to-do list.
Yeah, so I think it totally makes sense to look into, well, performance evaluation. I think it won't be easy in the sense that it won't be easy to compare to something. And so like, what's the reference point? Like, how can you say you are fast, right? Compared to what?
Yeah. So right now the goal isn't really to have a really fast network, but the exercise was more about, okay, we have a sorting network, and if we really look at it from a certain perspective, it looks like a dependency graph. Okay, let's try to implement it in a reactive programming language. So that's how we started with this idea. So it wasn't really about, oh, sorting networks, they're used in highly parallel systems. Let's try to make it even faster, and maybe we can use reactive programming. That wasn't our approach. So
maybe I can complete the answer. Historically, the performance of a sorting network is given by the depth of the network. If you have a bubble sort, that it's like the depth is n, whereas a bitonic sort is logarithmic in depth. So it's like the number of compare and exchange that you have to do in parallel in order to sort n wires to reach the end of the network.
Okay, thanks.
I have a question as well. So your language is point free, and that you have combinators to combine the different reactors. And it reminds me a lot of, for example, arrow combinators in Haskell work similar. You also have parallel composition, you have sequential composition, you have choice, like if then else, and you also have this distinction, which I find very interesting, between the deployment time and then the runtime variables. So they're distinct, and but then arrows in Haskell also have a point, or how do you say it? Well, a style that supports variable names for the individual values, and you can pass those values around. Basically, it's a bit more verbose, but it's sometimes also clearer, easier to read in some sense. And I wonder whether something like that is possible, or whether that's even interesting for you, or yeah.
So I'm really not an expert in arrowized FRP, but as far as I understand, all these arrow combinator operators, they really make use of the type system, which would make some types of weaving operators that we have really difficult to express with just arrows. On the other hand, I think arrows, as you can use arrow, wait, let me rephrase that. On the other hand, arrows in FRP still have like the two faces that are being interleaved. While your reactive code is doing stuff, you can still create new signals, not directly, but you can still trigger new signal combinations from being triggered, so to speak. And this is something that we do in our analysis at the deployment phase, such that we can still construct the full dependency graph.
Maybe if I can allow myself the comment. So you're certainly right that in arrowized FRP, there's like in Yampa, for example, which is also the first arrowized FRP framework. There's this dynamical switching where you can enter new signal networks, but it's not very specific to arrows itself, but rather to this library, or it's a speciality of this library. It's just a comment, but maybe it's interesting for you to see how a not point-free language could look like that has a similar philosophy of building up a dependency graph, a static one.
Yeah.
Okay, other questions?
Yeah, I have a question. So you have this snake operator, which can like feed the output to an input, right?
Mm-hmm.
And do you have anything like to prevent loops from happening? Like,
so because the deployment phase is actually the phase where I construct the complete dependency graph. So if I apply the snake operator to a reactor and that snake operator introduces a cycle, then I can just detect, you've made a cycle in the dependency graph. That's not allowed. I will just abort the program.
And I also have a comment about the types. So I'm not exactly sure that it's like that's limiting what you can do. Like, it seems like what you're doing in a language like Agda, it could just be like a library with all like all the guarantees that you want. But you do need like a fancy language like Agda to do it, I think.
I'm not familiar with Agda, so I can't really say anything about that.
But like probably all those rules that you're making, you can probably encode them in Agda.
No.
And then just reuse their type checker.
No. Okay, thank you.
It seems like this deployment phase, basically, maybe I can expand on what Adrian is saying. This deployment phase, it at least checks the shapes, or I don't know what your precise concept for that is. The shapes of the wires and of the reactors. It checks that, and it's and it might be possible that this is actually a language that you can bring in the form of a type system. Actually, I would expect that you can make a type system that contains these shapes, and then have a type checker do the checking whether the shape is allowed and isn't cycle free and so on.
Yeah, a type checker could definitely help. I'm not really sure of that right now, but yeah, it's possible.
Is there other questions? Okay, and also the time seems to be up, so thanks a lot, Björn, for this talk again, and we'll hear the closing remarks.
All right, so if you've just joined, I see that there's a few more people in the chat, and I also checked the YouTube channel. There were a few people watching there, like 10 or 15 before. There's the talk that was taking place at 4 in Eastern Standard Time is going to be canceled. So what we're going to do is we're just going to wrap up, and that way we all get to enjoy the rest of Splash without having to worry about coming here and so on. What's that, Wolf?
To sleep.
Okay.
We will be
or to sleep, yeah. You're
we'll be repeating our recoup paper, and I have to wake up at 5:30. So.
I saw that some people, it was 4 a.m. right in Japan or something.
Yeah.
So yeah, they probably want me to finish quickly. So now I just have a couple of words to say. So first, let me see if I can share my screen. There we go. So that's it. That's the end of the sessions. And first, I would like to thank you all for coming and for giving your talks, for sending the papers. Rebels has been a team effort, and this is a pretty large team, even though we have 7 papers and so on. There were about 40 people involved in making Rebels happen this year, and Rebels happens this year because the people that worked on Rebels before made an effort to make it happen the prior year and so on. So we're lucky to enjoy having an event that is becoming bigger every year, and in particular in a year like this that has had a very good number of submissions in spite of everything that's going on. So once again, I would like to thank everybody. I would like to thank the steering committee for being there the whole time and for always being willing to help and take time off your busy schedules. And just everybody in the PC, every author who submitted, and everyone who is on the line. And of course, the people at Splash who organized it, and the people at Sigplan that support us. And our wonderful speaker, Gianluis Colasso, who gave the keynote this morning. And just one more thing that I would like to say before I finish is, to me, what I saw today during this conference or during this workshop is that there's a lot of connections in the work that we're all doing, which is the whole point of having a workshop on reactive and event-based languages. But to the point that some of the comments were, I think that thing you're doing is similar to that other thing, or I think that work that you're doing by hand, you could leverage on this whole language or dependently typed language, or maybe you're just re-implementing this for which already exists a library and so on. So I would consider us really lucky if we manage to, in the near future, get new papers out of this work, or even get collaborations out of this work. I would be really happy if I see a paper published next year that emerged from this, and even that resulted from 2 people meeting at Rebels this year and saying, hey, let's talk about your work. So I invite you to continue the discussion, because the sessions end today, but Rebels continues. You still, you're still connected on Clouder. You can still message each other. So I would say continue those conversations. And I have already 5 people written down that I want to send messages to see if we can maybe work on a paper together or help each other in some way. And I invite you to do the same. So thank you very much. That's it for today. And I hope we get to see each other during Splash and also during a future Rebels. Thank you.
I think we should also thank our PC chair, Ivan, for doing a great job, for setting up the entire process, for reviewing, getting a PC committee together, and so on. So thank you, Ivan.
This was
Absolutely.
really a lot of
Thank you,
work, but thanks. That was amazing, especially this year. So good job.
Yeah.
Yes.
Okay. See you guys.
See you next year in person.
Hopefully.
Hopefully.
Yes.
Bye-bye.